Mentos, Nerds, and Skittles are engineered to hit your mouth with a perfect burst of taste. Inside high-speed candy factories, hot syrups become tiny pellets and precision flavor dosing locks in that signature snap. In this video, we go behind the scenes of each production line to see how these iconic sweets are formed and what tiny process tweaks make every candy taste exactly the same. Mentos start as a controlled balance between dry crystals and warm syrup. The goal at the beginning is simple: create a base that can be shaped without cracking, and then set it into a stable chew that will accept a hard shell. Sugar enters the line first, and it is treated as an engineered material rather than a sweetener. The crystals are screened so the size range is tight. That matters because the later mixing stage relies on predictable wetting. When crystal sizes vary too much, the small particles hydrate fast and the large particles stay dry. That creates weak zones that show up as gritty texture or uneven bite. In parallel, a glucose-based syrup is held at a steady temperature in jacketed tanks. The heat keeps the syrup flowing like a thick liquid instead of a slow gel. Pumps push it through filters and meters that smooth out pulsations. The entire point is to deliver the same flow every second. If the syrup surges, the candy core becomes soft. If it starves, the core becomes crumbly. Dry minor ingredients join through feeders that behave like precision valves. Texturizers such as starch are added to control stickiness during forming. Acidulants are added to tune brightness and to steer how the sugar phase behaves during conditioning. Very small additions are blended upstream so they do not land as streaks in the mass. The streams meet inside an enclosed mixer where wetting is forced to happen quickly. Paddle elements sweep the walls and fold the mass through itself. The mixture passes through stages that look like dry sand at first and then like damp granules. As mixing continues, the granules begin to bind. The syrup coats the crystals and bridges them into a cohesive feed for the next machine. From the mixer, the material enters a continuous conditioner. This is where heat and shear begin the real transformation. The mass is kneaded while the temperature rises in controlled steps. Some of the sugar dissolves into the syrup phase. The remaining crystals stay intact and act like structural filler. That blend is what gives the final core its specific chew. Too much dissolution makes a rubbery bite. Too little dissolution makes a brittle bite. A vacuum section often follows to pull out trapped air. Air pockets are small, but they matter. They create internal voids that can collapse during coating. They also reduce density, which changes how pieces roll in later drums. When the air is removed, the mass becomes smoother and more uniform. Next comes forming, and this is where the process starts to look like candy rather than paste. The plasticized mass is pushed through a die to create a continuous rope. The rope has a defined diameter that matches the final piece width. A set of rollers or calibration guides controls the rope surface so it does not twist or flatten. The rope moves directly into a cutting unit that portions it into pellets. The cut timing is locked to belt speed so every piece has the same length. The cut faces are still fresh and slightly tacky. That tack is useful because it allows the next step to round the shape without cracking the surface. The pellets enter a rounding stage where they tumble and roll against each other. The motion knocks off sharp edges and forces the surface to smooth. Friction warms the outer layer just enough to seal micro cracks. The goal is a dense core with a consistent geometry. That geometry is critical because the shell builds evenly only when each core rolls the same way. After shaping, the cores must be conditioned before coating. They travel through controlled air sections that adjust temperature and moisture. This step prevents shell defects later. If the core is too warm, the first shell layers dissolve and smear. If the core is too dry, the first layers do not bond well. Conditioning brings the cores to a stable state where the surface is firm yet receptive. When the cores reach coating, they enter large rotating pans or perforated drums. The core movement is constant and it is carefully tuned. The bed depth and rotation speed control collisions. Collisions must be strong enough to keep pieces separated. They must not be so strong that they chip the still forming shell. The shell is built in layers rather than one application. A coating solution is sprayed as a fine mist across the moving bed. Immediately after spraying, a dry powder is often dusted in. Airflow then removes moisture, so the layer sets before the next one arrives. This spray and dry cycle repeats many times. Each cycle adds only a thin film. Layering avoids cracks because stress is distributed gradually. At the start of coating, the syrup phase is more forgiving. It acts like an adhesive primer that locks onto the core surface. As cycles continue, the composition shifts toward harder sugar-based layers. The process gradually moves from bonding to building. The shell thickens and becomes the structure that gives the candy its snap. Drying is not just about removing water. It is about controlling how crystals form. Fast drying can trap moisture inside and create a brittle outer skin. Slow drying can let the surface stay tacky and cause pieces to stick together. The airflow temperature and humidity are tuned, so crystallization happens evenly through the growing shell. As thickness increases, the process focuses on smoothness and roundness. The spray pattern is adjusted so no side gets more liquid than another. The drum motion is adjusted so pieces roll rather than slide. Rolling is what builds a uniform shell. Sliding creates flats and ridges that later show up as rough mouthfeel. Color and flavor can be introduced at specific points in the shell build. Early addition drives deeper penetration into the outer layers. Late addition keeps aroma closer to the surface. Timing is used as a control knob. It shapes how quickly the flavor is released when the candy is chewed. Once the shell has reached its target mass, the finish steps begin. A final smoothing phase uses lighter sprays and longer dry time. This reduces micro texture and tightens gloss. Then a polishing agent is applied in a thin film. The agent spreads under tumbling and fills tiny surface pores. The result is a clean shine and reduced friction, so pieces do not scuff in handling. The coated candy now needs final equilibration. It is held in bins or conditioning rooms where moisture equalizes between core and shell. This reduces internal stress. Without this step, the shell can craze. Crazing looks like fine cracks, and it can grow during storage. Quality checks happen along the line, but the main process signals are physical. Size distribution is checked because coating mass depends on surface area. Shell thickness is checked because it controls crunch and dissolution rate. Hardness is checked because it reflects both moisture and crystal structure. Surface inspection looks for chips and twins. Twins are two pieces stuck together during coating. When the product is cleared, it moves to packaging. The candy is conveyed to weighers that portion exact amounts. The flow properties matter here too. The polished shell helps the pieces slide and settle. Multi-head weighers use many small hoppers to assemble a target weight with minimal deviation. The measured portions drop into form-fill seal machines or cartoning systems depending on format. Film is formed into a tube and sealed. The drop is timed so pieces fall cleanly without crushing. Seals are made with controlled heat so the film closes without wrinkles. If cartons are used, the candy is fed into inner packs and then into outer sleeves. Nerd's Candy is built by turning concentrated flavored sugar syrup into a porous sheet, then fracturing that sheet into tiny irregular crystals, then sorting and finishing those crystals so each piece stays sharp and dry. Production starts with raw sugar management because particle size and purity drive how the syrup cooks. Granulated sugar is conveyed from bulk storage into day bins that feed the dissolving system. Screens remove oversized crystals and fines to keep dissolution predictable. Magnets and strainers protect downstream pumps and valves from metallic debris. A second carbohydrate stream is prepared to control viscosity and inhibit unwanted crystallization during cooking. Corn syrup is warmed in jacketed tanks until it reaches a stable pumping consistency. Flow meters and control valves keep corn syrup delivery steady across the run. Water is filtered and tempered so it enters mixing at a consistent temperature. Dry acids are staged in sealed hoppers so they remain free-flowing. Citric acid and malic acid are kept separate until late addition because acid affects inversion and color stability. Salt and buffering salts are staged in microfeeders when the recipe calls for them. Flavor concentrates are prepared in small tanks with controlled agitation so they stay homogeneous. Color solutions are diluted to a dosing range that avoids banding and streaking. The line splits early into two parallel syrup paths because Nerds typically pairs two flavors and two colors. Each path has its own dissolving and cooking controls, even if both share utilities. This separation lets each flavor reach its own target acid and aroma level without compromise. Sugar dissolution begins in a heated dissolver where sugar and water form a high solid slurry. Agitators sweep the vessel walls to prevent sugar crust. The slurry is heated until it becomes a clear solution. Inline strainers remove undissolved particles that would seed crystals too early. The solution flows to a balance tank that evens out feed rate to the cooker. Concentration is driven by a continuous cooker that raises temperature and removes water. Many lines use a coil or plate heat exchanger followed by a flash stage. The syrup enters under pressure so it can reach high temperature without boiling. The flash section drops pressure and releases water vapor in a controlled burst. This step tightens final moisture and improves consistency. Bricks and temperature are monitored constantly because small shifts change how the candy fractures later. A higher final moisture yields a tougher sheet that breaks into larger chunks. A lower final moisture yields a brittle sheet that shatters into dust. The target sits in a narrow window that supports clean fracture with limited fines. Corn syrup is injected at a controlled point to tune glass transition and reduce uncontrolled graining. The injection location matters because early addition changes cook behavior. Late addition can preserve more of the corn syrup function as a plasticizer. The syrup then passes through static mixers that eliminate streaking. Acid addition is handled carefully because acid can catalyze sucrose inversion during heat exposure. Many processes add acid after the hottest zone to limit inversion. The acid is metered as a solution to ensure rapid dispersion. Inline pH measurement is used in some lines as a confirmatory control. This stage sets the tart backbone that defines the flavor profile. Flavor and color are added after temperature is reduced to protect volatile compounds. A cooling loop drops syrup temperature to a range where aromas survive. Flavor oils are dosed through precision pumps into a turbulent region. Emulsifiers may be included, so oil-based flavors stay evenly distributed. Color is injected with high shear mixing, so each path produces uniform hue. The two flavored syrups now need to become solid candy in a form that can be fractured. One common approach is slab casting or film casting onto a cooled surface. The syrup is deposited as a thin ribbon onto a moving stainless belt. Belt speed and deposit rate set film thickness. Cooling plates beneath the belt pull heat out rapidly and evenly. As the film cools, it becomes a glassy sheet rather than a soft mass. Rapid cooling prevents large crystals from forming. The goal is an amorphous structure with controlled microcrystallization later. The sheet is guided through a cooling tunnel where air temperature and velocity are controlled. Surface moisture is kept low, so the sheet does not pick up tack. Some processes encourage controlled graining after initial set. This can be done by seeding or by mechanical working. Light agitation or flexing creates internal stress sites that guide fracture. The sheet may pass through a scoring station that introduces shallow grooves. Grooves create predictable breakpoints and reduce random oversized lumps. Once the sheet reaches a target, brittleness, it is released from the belt. A scraper blade lifts the sheet edge and directs it into a breaker. The breaker uses toothed rollers or oscillating bars to crack the sheet into pieces. The first break aims for chips that are still larger than the final candy size. This staged reduction avoids excessive dust creation. The chips move into a milling and crushing system that creates the nerd's granule size. A common setup uses roll crushers that apply compressive force. Roll gap controls the size distribution and also controls the amount of fines. Too tight a gap makes powder and reduces yield. Too wide a gap leaves chunks that do not feel like nerds. After roll crushing, the material enters a vibrating screen deck. Screens separate into multiple fractions in one pass. The target fraction is routed forward as product stream. Oversize is returned to the crusher for another pass. Fines are collected as a separate stream for rework or controlled reuse. The system is tuned to make irregular shapes rather than uniform spheres. Irregular shapes create the characteristic crunchy texture. The fracture surfaces must remain sharp and dry. Rounded surfaces would suggest coating that is too heavy or milling that is too aggressive. Because nerds often includes two flavors. In one pack, the line must keep colors separated until final blending. Each flavor color runs through its own crushing and screening loop. This prevents color contamination in recycle streams. It also allows each flavor to use its own target brittleness. Some flavors require slightly different moisture to break cleanly. Once each color is sized, it moves into conditioning bins. Conditioning allows moisture gradients to equalize inside each granule. Equalization reduces later caking in storage. It also stabilizes crunch by keeping the candy in a glassy state. Airflow in these bins is controlled to prevent humidity pickup. At this stage, the candy may receive a very light finishing step to improve flow. A tiny amount of anti-caking agent can be applied as a dry dust. The goal is to reduce surface stick points without changing texture. Application is done in a tumbler where powder distribution becomes uniform. Excess powder is removed by aspiration, so the finish remains minimal. Some formats use an additional micro-coating for color stability or acid placement. This can be done by misting a dilute syrup and then drying quickly. The mist acts as a binder for a fine acid layer or a color adjust layer. Drying must be fast so the granules do not fuse together. The micro-coating is kept thin to avoid rounding edges. If the recipe calls for a stronger sour hit, the acid can be partially surface loaded. Surface loading is done after sizing so the acid stays near the exterior. This approach changes perception because acid dissolves immediately. It also requires careful humidity control because acids can pull moisture. Granules are then blended to match the intended mix ratio. A gravimetric. Blending system meters each color stream. The blender uses gentle paddles or ribbon elements that avoid crushing. The objective is homogeneous distribution without generating new fines. Sampling at the blender outlet confirms color ratio across time. Transfer to packaging requires stable flow behavior. Granules can bridge if humidity rises or if fines increase. Hoppers are designed with steep walls and vibration options. Feed screws or vibratory feeders deliver candy into multi-head weighers. Weighers build target weights by combining small hopper dumps. Packaging format changes the final handling steps. In small boxes, the granules drop into cartons through a funnel system. Carton fill height is controlled to avoid crushing at the edges. In bag formats, the candy drops into a forming tube and then into sealed film. Seal timing is synchronized with the drop to keep granules out of seal areas. Some products use dual chamber packaging that keeps flavors separated until pouring. Dual chamber designs require 2 parallel weigh and fill lanes. Each lane fills its own side of the package. A split-forming collar shapes the film into 2 channels. Seals create a central divider that remains intact. For mixed packs that combine 2 flavors in one cavity, the blender feeds a single weigher. The weigher controls portion size and drop accuracy. Drop height is minimized to reduce fragmentation. Chutes are designed with low friction surfaces to prevent hang-ups. Coding and inspection happen after sealing and closure. Vision systems can verify fill presence and detect seal contamination. Weight checks confirm package mass within tolerance. Reject systems remove outliers without stopping the line. Finished units are then collated into cases. Case packing is designed to limit vibration that could create dust. Cartons or bags are grouped and then dropped into corrugated cases. Cases are closed and sealed with tape or adhesive. Pallet patterns are chosen to reduce compression on lower layers. Skittles candy is made by building a chewy flavored center and then growing a crisp sugar shell that carries color and gloss. The process is a long chain of controlled transformations. It begins with dry powders and syrups that are treated like engineering feedstocks. It ends with uniformly sized pellets that flow through packaging equipment without sticking. The first stage is ingredient staging and metering. Granulated sugar is unloaded into silos and routed through screens that narrow the crystal size range. Consistent crystal size keeps dissolution predictable during cooking. Glucose syrup or corn syrup is held in heated tanks so it can be pumped at a stable flow rate. Water is filtered and tempered so it enters the system at a repeatable temperature. Minor ingredients are staged in sealed bins and then moved to microfeeders. These microfeeders meter acids and salts and functional powders with high precision. The center of a Skittles piece starts as a cooked candy base that will later be plasticized into a chew. Sugar and water first meet in a dissolving system that prevents dry clumps. Agitators create a strong vortex and pull crystals into solution. Heat raises the mixture to speed dissolution while avoiding localized scorching. The goal is a clear syrup with no undissolved grains. Inline strainers remove stray solids that could seed crystals later. The syrup then flows into a balance tank that smooths out any upstream fluctuations. From the balance tank, the syrup feeds a continuous cooker. The cooker raises temperature quickly to drive off water and concentrate solids. Many lines use pressurized heating, so the syrup can reach high temperature without boiling in the coil. After heating, the syrup enters a flash stage that drops pressure. Water vapor leaves instantly and pulls heat out at the same time. This step locks in final solids content and sets the base viscosity for the next stages. Solids content is tracked constantly because it affects chew texture and forming behavior. If moisture is too high, the centers stay soft and can deform during shell building. If moisture is too low, the centers become brittle and can crack under tumbling loads. Temperature is controlled with tight limits because viscosity changes rapidly with heat. Flow meters and control valves keep feed rate steady because residence time in the cooker must remain stable. After concentration, the hot syrup is cooled to a controlled temperature before sensitive ingredients are added. Cooling happens in a scraped surface exchanger or a plate heat exchanger. Scraped surfaces are used when viscosity is high and fouling risk increases. The cooled syrup enters a mixing manifold where functional additions are injected. Acids are added at this stage to manage flavor brightness and to set the target pH. Adding acid after the hottest zone reduces unwanted sucrose inversion. Flavor addition is handled as a separate system because flavors can be volatile and unevenly dispersing. Oil-based flavors are prepared as emulsions or are blended with carriers. Water-soluble flavors are diluted to a pumpable concentration. Both are dosed through metering pumps into a turbulent section of the stream. Static mixers fold the flow repeatedly to eliminate streaks. The objective is to make every portion of the candy base taste identical within a batch. Color is not usually placed in the center for a classic Skittles style. The center can remain neutral or lightly tinted depending on product type. This choice keeps the center stable and lets the shell carry the signature color identity. Even when the center is neutral, it must still be consistent in density and moisture. That consistency keeps shell growth uniform and prevents weak adhesion areas. The cooked and flavored mass now moves into a forming system. At this point, the material behaves like a thick plastic melt. It must be shaped into small pieces that will become the final candy cores. Extrusion is a common forming method for this kind of center. The mass is pushed through a die plate to create multiple ropes at once. Each rope has a controlled diameter that matches the planned final piece size after shell growth. As the ropes exit the die, they are cut into pellets. Cutting uses rotating knives or wire cutters synchronized to line speed. The cut length defines the initial core mass. Tight control is critical because shell thickness is added on top of the core. If core mass varies, then final piece mass varies, even if shell growth is perfect. The freshly cut pellets are soft and tacky. They must be conditioned quickly so they do not fuse together. Pellets transfer to a preconditioning conveyor or a cooling drum. Cooling air removes surface heat and firms the outer layer. The cooling profile is chosen to avoid a hard skin with a soft interior. A hard skin can crack during tumbling and expose a sticky interior. A uniform set keeps the pellet resilient during handling. The pellets may pass through a light dusting stage that prevents sticking. The dust is minimal and it is chosen to avoid changing flavor. Shaping continues with rounding. Pellets tumble in a rotating drum where they collide and roll. The motion rounds edges and smooths cut faces. Friction and gentle compression help the surface seal. The goal is a compact core with a slightly elastic bite. This elastic bite is what defines the chew under the later crisp shell. Rounding also improves how pieces roll in coating pans. Uniform rolling produces uniform shell thickness. After rounding, the cores undergo a rest stage. Rest allows moisture and temperature to equilibrate through the core. This reduces gradients that can cause deformation later. The cores move through conditioning bins with controlled airflow. Air temperature and humidity are adjusted so the core surface becomes dry enough for coating adhesion without becoming brittle. Moisture content is measured or inferred from process correlations. The process aims to keep the core in a stable glassy or rubbery state depending on formulation. Now the line transitions into shell building. Shell building is where Skittles develops its hard, crunchy outer layer. The cores enter large rotating coating pans or perforated coating drums. Rotation makes the bed of cores circulate in a continuous wave. Cores climb and then slide or roll down the moving bed. That rolling action exposes all surfaces to spray and to drying air. Shell growth happens in cycles. Each cycle applies a thin layer of syrup and then removes water to crystallize that layer. A spray system atomizes a sugar solution into a fine mist. Droplets land on moving cores and form a wet film. Almost immediately, dry air flows through the bed to evaporate water. As water leaves, the dissolved sugar crystallizes and locks into a solid layer. The drum continues rotating, so pieces do not stick to each other while wet. On relentless factory lines, where timing and temperature decide everything. Molten chocolate cascades through molds, while caramel and crisp centers are coated and cooled by machines running at astonishing speed. In this video, we go behind the scenes to uncover how non-stop automation transforms simple ingredients into instantly recognizable candy icons like M&M's, Twix, and Snickers. M&M's production begins with the manufacturing of the chocolate core. Each milk chocolate center is formed by molding a precise deposit of tempered chocolate onto a cooling belt. Chocolate mass is created by blending sugar with cocoa liquor and milk solids in a high-capacity mixer. This blend is refined through a 5-roll mill that reduces particle size to below 30 microns. The refined paste is moved to conching tanks where it is mixed and aerated at a temperature of 55 degrees Celsius. Lecithin is added as an emulsifier to achieve a smooth, flowable texture. The conched chocolate is held in jacketed tanks to maintain a liquid state. It is tempered using a 3-stage tempering unit which cycles the chocolate through controlled heating and cooling to form stable crystal structures. Tempered chocolate is pumped to a depositor that releases metered drops onto a stainless steel belt moving through a cooling tunnel. The belt temperature is kept between 5 and 10 degrees Celsius to solidify the chocolate in less than 60 seconds. The formed centers are demolded mechanically and stored in buffer bins before the next process. For peanut M&Ms, the process begins by dry roasting raw peanuts in continuous belt roasters. Roasting temperature is maintained at 160 degrees Celsius for 20 minutes. Peanuts are then cooled by ambient air in a vibrating cooler. After cooling, they pass through a sizing unit that removes undersized or broken nuts. The selected peanuts are fed into panning drums where chocolate is applied in successive layers. Each drum rotates at a fixed angle and speed to ensure uniform tumbling. A measured amount of chocolate is sprayed onto the surface of the peanuts using heated nozzles. After each application, cold air is blown into the drum to partially solidify the layer. This process repeats until the peanuts reach a target diameter. The final chocolate coating is smoothed using a polishing pass with minimal chocolate to eliminate surface irregularities. Crispy M&Ms are built around an extruded rice core. Rice flour and corn grits are mixed with water and processed through a twin-screw extruder. The extruded dough is cut into uniform pellets using a rotating blade. Pellets are puffed in a high-temperature expansion chamber. After expansion, they are dried in a convection dryer, then coated with a thin film of fat to reduce moisture absorption. The puffed cores are enrobed in chocolate using the same panning method applied to peanuts. All chocolate-coated centers are transferred to the sugar coating area. The process starts in large rotating pans where the cores are sprayed with a sugar solution. The sugar syrup consists of sucrose water and glucose and is delivered at a constant temperature of 75 degrees Celsius. Each spray cycle is followed by a drying cycle that circulates dehumidified air around the rotating bed of centers. Sugar builds up in fine layers over dozens of cycles. The panning operator adjusts spray volume drum rotation speed and airflow to maintain uniformity. Once the sugar shell reaches the desired thickness, color is applied. Coloring is done by mixing food dye with shellac and carnauba wax to produce a glossy, tinted coating. The colorant is misted onto the sugar-coated centers in a fine spray. Multiple passes may be required for dark colors like red or brown. After coloring, the coated pieces are polished with a dry mixture of shellac and wax. This step is performed in polishing pans, rotating at low speed. The polishing agent adheres to the surface and is distributed by friction between the tumbling pieces. The resulting finish is smooth, hard, and glossy with highlight reflectivity. Polished M&Ms are discharged from the pans and moved to a conditioning silo. This silo is temperature and humidity controlled to allow the coating to fully harden and stabilize. Residence time in the silo is typically 2 to 4 hours depending on coating thickness. After conditioning, the candies are conveyed to the printing station. The iconic letter is applied using offset graver printers. Each piece is positioned in a dimpled conveyor plate with cavities sized to hold one candy. The plate passes beneath a print head which uses edible white ink. The print roller is engraved with the letter M and rotates in sync with the conveyor. Contact pressure is controlled pneumatically to ensure legibility without damaging the shell. Printed candies are inspected by machine vision systems that detect missing or malformed prints. Unmarked units are removed by air jets and recycled into the system for reprinting. Approved units continue to the packaging stage. The candies are weighed and dosed using multi-head combination weighers that drop exact quantities into vertical form fill seal machines. Packaging film is pulled into the forming collar and sealed into a tube. The bottom is sealed with a heated jaw and the product is dropped in. The top seal is then applied, creating a pillow pack. Filled packages are conveyed to check weighers that verify compliance with weight specifications. Any over or underweight packs are removed automatically. From start to finish, the process involves sequential mechanical operations that include mixing, depositing molding panning, spraying printing, and sealing. Each unit operation is tuned to specific parameters that ensure dimensional consistency and coating integrity. The manufacturing line is modular, with separate zones for chocolate handling, core preparation, sugar coating, and final packaging. Mass flow is maintained using belts, pneumatic conveyors, and elevators that transfer product between levels. The entire line is integrated by a control system that monitors temperature, flow rate, viscosity, and speed at each point. Adjustments are made automatically through feedback loops that maintain constant output. There are no batch holds once the system is running. The chocolate centers flow continuously through coating, coloring, and packaging without pause. Sugar solutions are replenished through a bulk feed system with inline heating and mixing. Chocolate is tempered in a loop with real-time viscosity monitoring. Each candy undergoes a transformation that begins with a molten mass and ends with a layered composite structure. The core is solid or puffed depending on type. The first layer is tempered chocolate applied by drum enrobing. The second layer is crystalline sugar formed by sequential syrup application and drying. The third layer is colorant and wax forming the glossy finish. The fourth step is marking with the printed letter. All coating is additive applied in micro-thin layers, controlled by time rotation and fluid volume. There is no molding of the outer shape. The spherical form is achieved through cumulative coating and mechanical tumbling. The smoothness is the result of abrasion polishing and repeated layering under rotation. Thermal inputs are limited to chocolate tempering, syrup heating, and ambient conditioning. No baking, frying, or high temperature processing occurs. Moisture is carefully controlled during sugar coating to avoid bloom or crystallization defects. Every part of the process is dry, except the syrup spray and initial chocolate melt. Mechanical design of the panning drums ensures even exposure for each piece. Drum material is stainless steel with ribbed interiors that increase mixing efficiency. Air delivery systems are connected to each drum to maintain controlled drying. The air is filtered, cooled, and dehumidified before being directed at the product. Timing across the system is synchronized by programmable logic controllers. Every depositor, cutter, printer, and packager is indexed to match upstream flow. Any stoppage triggers a cascading halt to preserve continuity. Materials are buffered at key points to allow restart without waste. Twix production begins with controlled preparation of the biscuit base that defines the structure of the bar. Twix biscuit dough is created by feeding wheat flour into a continuous mixing system. The flour is combined with sugar and vegetable fat inside a horizontal mixer. Mixing paddles rotate at low speed to coat flour particles with fat. Water is added in measured flow to bind the mixture into a cohesive dough. Dough temperature is regulated to maintain firmness during shaping. The mixed dough exits the mixer and enters a feed hopper that supplies the forming line. The dough is transferred onto a rolling table, where compression rollers flatten it into a continuous sheet. Roller gap settings determine final biscuit thickness. The sheet passes through alignment guides that maintain straight edges. A rotary cutting drum imprints the dough into uniform rectangular segments. Excess dough is removed and recycled upstream. The shaped dough pieces are placed onto a steel mesh conveyor for baking. The baking stage uses a tunnel oven with multiple heating zones. The conveyor transports dough pieces through gradually increasing temperatures. Initial zones dry the surface without browning. Middle zones promote internal structure development. Final zones create golden coloration and crisp texture. Oven airflow is directed above and below the conveyor. Baking time is adjusted to control moisture content. The baked biscuit bases exit the oven with stable shape and strength. Freshly baked biscuit bases move directly into a cooling tunnel. Ambient and chilled air flow reduces biscuit temperature. Cooling prevents caramel deformation during later stages. Conveyor speed maintains spacing between pieces. The biscuits emerge cooled and rigid. They are aligned into lanes for caramel application. Caramel production occurs in a separate continuous system. Glucose syrup flows into a preheating chamber. Milk solids and sugar are added under agitation. The mixture passes through a vacuum cooker. Reduced pressure lowers boiling temperature. Moisture evaporates rapidly to thicken the caramel. Cooking parameters define final viscosity. The caramel exits the cooker as a smooth, elastic mass. Cooked caramel is transferred into a holding vessel. Slow agitators prevent crystallization. The caramel is pumped through heated pipes to the depositor. The depositor contains multiple nozzles aligned with biscuit lanes. Each nozzle dispenses a precise ribbon of caramel. Deposition rate controls caramel height. Temperature ensures proper flow and adhesion. Caramel-coated biscuits move through a setting tunnel. Cool air partially solidifies the caramel layer. The caramel becomes firm enough to hold shape. The biscuits continue along the conveyor without distortion. The caramel surface remains tacky for chocolate bonding. Chocolate coating begins with preparation of milk chocolate. Cocoa mass, sugar, milk powder, and cocoa butter are blended. The mixture is refined to reduce particle size. Conching develops smooth texture. Finished chocolate is transferred to tempering units. Tempering controls crystal formation. Chocolate reaches a stable liquid state. Tempered chocolate flows into the enrobing machine. A continuous chocolate curtain forms across the conveyor. Biscuit caramel assemblies pass beneath the curtain. Chocolate coats the top and sides evenly. A bottoming system coats the underside through the mesh belt. Excess chocolate drains back into the system. Air knives shape the chocolate layer. Gentle vibration removes bubbles. The coating thickness becomes uniform. Decorative surface lines may form naturally from airflow. The enrobed Twix bars enter a cooling tunnel immediately. Cooling tunnels use staged temperature zones. Initial zones prevent surface cracking. Later zones fully crystallize the chocolate. Air velocity ensures even cooling. Belt speed defines dwell time. The chocolate shell hardens around the biscuit and caramel core. After cooling, the bars exit with rigid structure. The bars are transferred to the splitting station. Twix bars are cut lengthwise into twin fingers. Servo-controlled blades ensure precise separation. Each finger maintains identical dimensions. Separated Twix fingers are aligned on packaging conveyors. Spacing belts organize the flow. The bars enter flow wrapping machines. Packaging film is fed from large rolls. The film wraps around each finger. Longitudinal seals are formed by heated rollers. End seals are created by rotating jaws. Wrapped fingers are paired for twin pack format. Collation belts bring two wrapped fingers together. The paired unit is wrapped again or inserted into an outer sleeve. Wrapping speed matches upstream production. The sealed packs exit the line in continuous flow. Throughout Twix, manufacturing every step is synchronized. Conveyor speeds coordinate with deposition rates. Thermal stages are sequenced to avoid overlap. Mechanical forming ensures consistent geometry. Material flow remains uninterrupted from dough to wrapper. The biscuit base provides rigidity. The caramel supplies chew and adhesion. The chocolate delivers coating and protection. Each layer is applied in a defined order. Temperature control maintains layer integrity. Timing ensures bonding without deformation. Twix production operates as a linear system. Dough shaping precedes baking. Baking precedes caramel deposition. Caramel setting precedes chocolate enrobing. Chocolate cooling precedes cutting and wrapping. Each stage depends on the previous one. Ingredient transformations are mechanical and thermal. Dough changes through heat exposure. Caramel thickens through evaporation. Chocolate crystallizes through controlled cooling. No stage reverses a previous transformation. The biscuit sheet thickness defines bite texture. Caramel viscosity defines chew resistance. Chocolate thickness defines snap. These variables are adjusted through machine settings. No manual shaping occurs after initial dough forming. Continuous monitoring of belt alignment prevents product drift. Sensors maintain spacing accuracy. Pump pressures control flow stability. Roller speeds define forming precision. Each parameter is linked to output consistency. Twix bars emerge fully assembled before packaging. The layered structure remains intact. The product shape remains constant across units. The manufacturing line produces thousands of bars per hour. Output remains uniform due to synchronized automation. Every Twix bar follows the same physical path. Raw materials enter as powders and liquids. Finished bars exit as layered chocolate products. The process relies on controlled movement. Thermal transitions define each stage. Mechanical handling preserves structure. Snickers bars are built in layers, starting with the nougat foundation. The nougat is produced by combining sugar, corn syrup, and milk powder in a heated mixing vessel. These ingredients are blended and cooked until they form a thick paste. A separate stream of whipped egg whites is prepared using high-speed beaters. The aerated egg white mass is gradually folded into the hot sugar mixture. This step introduces air cells and creates the spongy texture of the nougat. The blending continues until the mixture reaches uniform density and viscosity. The final nougat mass is held in a feed tank equipped with slow paddles to prevent collapse. The nougat is deposited as a continuous slab onto a moving belt. The belt is lined with a non-stick material to allow clean release. A leveling roller spreads the nougat to the target height. Guide rails control the slab width. The slab is conveyed into a cooling chamber to set the structure. Chilled air circulates around the slab until surface temperature drops below 15 degrees Celsius. The cooled nougat slab exits the chamber with a firm texture and is ready for the next layer. Caramel is prepared in a separate cooking line using glucose syrup, milk fat, and sucrose. These ingredients are fed into a continuous cooker with steam-heated zones. The mixture is heated to reduce water content and initiate Maillard reactions. Caramelization develops flavor and viscosity. The cooked caramel exits the vacuum chamber and enters a holding tank. The tank is agitated slowly to maintain homogeneity and prevent crystallization. The caramel temperature is maintained near 60 degrees Celsius for optimal flow. Roasted peanuts are prepared separately. Raw peanuts are roasted in a forced air roaster where temperature is held between 160 and 180 degrees Celsius. Roasting continues for 20 minutes until internal moisture falls below 2%. The peanuts are cooled by ambient air, then passed through a vibrating grater. Oversized and broken peanuts are removed. The accepted peanuts are stored in silos connected to the deposition system. Caramel is deposited onto the cooled nougat slab using a curtain-style applicator. The applicator spans the full width of the slab and releases caramel in a uniform layer. Flow rate and belt speed are adjusted to control caramel thickness. Directly after caramel application, roasted peanuts are dropped from a vibratory feeder. The feeder spans the same width as the slab. A controlled quantity of peanuts is dispensed and embedded into the caramel by a light compression roller. This roller presses the nuts into the surface to ensure mechanical bonding. The multi-layer slab is conveyed through a second cooling tunnel. The tunnel has temperature zones starting at 12 degrees Celsius and ending at 6 degrees Celsius. Chilled air is circulated above and below the belt to harden the caramel. Dwell time is calibrated to match the slab thickness and maintain shape stability. The slab exits the tunnel with a cohesive structure and defined layers. A guillotine cutter slices the multi-layer slab into narrow lanes. The cutter uses servo-controlled blades aligned with the slab width. The lanes are transferred onto narrower belts for portioning. Another guillotine cuts the lanes into bar-length segments. Blade speed and belt speed are synchronized to ensure uniform bar size. Each segment is now a complete core containing nougat, caramel, and peanuts. The bar cores are spaced and oriented for enrobing. They enter the chocolate coating system in a single file. Milk chocolate is melted in a jacketed tank and tempered in a continuous flow unit. The tempering process includes heating to melt all crystals, cooling to initiate stable crystal formation, and reheating to a precise working temperature. The tempered chocolate flows into a pump system that feeds the enrober. Each bar passes under a chocolate curtain that coats the top and sides. The base of each bar contacts a chocolate-coated roller or is sprayed from below. Chocolate flow is adjusted by modifying pump speed and curtain width. Excess chocolate is removed by a vibrating section that shakes the belt gently. Air knives apply a controlled stream of air to smooth the surface and reduce buildup. The coated bars enter a cooling tunnel to crystallize the chocolate. The tunnel has multiple zones with decreasing temperatures. Airflow is directed to maintain even cooling without condensation. The bars are conveyed for a fixed duration to complete the chocolate setting process. The final chocolate shell is solidified and stable upon exit. Each Snickers bar is now fully assembled and coated. Bars are aligned for wrapping using guiding rails and spacing conveyors. Flow wrappers are fed with printed film from a reel. The film is shaped into a tube around each bar. Heat sealing rollers create the longitudinal seam. Rotating jaws apply end seals. Seal pressure and temperature are monitored to match film type. The wrapped bars are conveyed into collection bins or directly to packing systems. Depending on product format, bars may be grouped into single, twin, or multi-pack configurations. Grouping conveyors align the bars into sets. Mechanical pushers or robotic arms load the grouped bars into cartons. Cartons are formed from flat blanks and glued using hot melt adhesive. Cartons are closed and sealed at the final station. No manual intervention is used during shaping, layering, cutting, or wrapping. All movements are performed by synchronized mechanical systems. Sensors monitor product position and spacing. Feedback loops adjust flow parameters. Each bar follows the same linear path from ingredient feed to final wrap. Nougat provides internal volume and structural support. Caramel binds the peanuts and delivers chew. Peanuts create inclusion texture and flavor variation. Chocolate forms an outer shell that locks the layers in place. Each component is manufactured and applied in discrete steps. Thermal and mechanical conditions are optimized for each transition. The slab format enables high-speed processing. Layering occurs in continuous motion. Cooling is integrated between each stage to preserve geometry. Cutting is servo-synchronized to belt speed. Chocolate tempering is calibrated to match bar throughput. Wrapping systems operate at matched cadence to upstream enrobing. Ingredient flow is regulated by volumetric pumps, gravity feeders, and temperature-controlled tanks. Mixing occurs in closed vessels with integrated agitators. Heat is applied via indirect steam or electric jackets. Each process vessel is isolated by flow valves and sensors. Conveyor systems link every step of the process. Belt widths and speeds are chosen to prevent jamming and maintain alignment. Transfer points are angled to reduce impact and preserve bar shape. Side guides and rollers keep products centered. Accumulation zones provide buffer capacity between stages. The system supports continuous operation without backtracking. Each bar is formed from base to wrap in a single direction. Mechanical shaping precedes deposition. Deposition precedes cutting. Cutting precedes coating. Coating precedes cooling. Cooling precedes wrapping. Every phase transforms material by specific mechanical or thermal means. Mixing combines dry and wet. Cooking removes water. Depositing creates form. Cooling fixes structure. Cutting defines unit size. Enrobing applies the shell. Wrapping seals the finished form. The Nerds production process begins with the selection and preparation of the sugar crystal cores. Unlike many candies that use molded or extruded centers, Nerds start with what are essentially coarse grains of sugar, clean, dry, and free of additives. These tiny sugar granules are screened to ensure uniform starting size. They must be small enough to grow consistently in a panning environment, yet large enough to withstand dozens of successive syrup applications without dissolving prematurely or becoming structurally unstable. The sugar cores are transported via vibratory feeders into stainless steel holding hoppers, where they await transfer to the coating pans. The pans used in Nerds production are large, tilted, rotating drums, often made of polished stainless steel or copper-lined interiors, mounted on motorized axles. Each pan is loaded with a pre-measured volume of sugar cores, and as they begin to rotate, the motion causes the particles to tumble and circulate continuously, exposing all surfaces evenly. This rotation is crucial. It ensures that every granule is coated uniformly on all sides, preventing clumps, deformities, or pooling. As the pan turns, a fine mist of sugar syrup is sprayed into the chamber using precision-controlled nozzles mounted near the drum's edge. This syrup, the heart of Nerds' layering process, is a concentrated solution of sugar and water, cooked to a specific temperature that ensures viscosity without excessive runniness. It's critical that each application is delivered in ultra-fine mist form. If too much syrup is added at once, the granules will clump or flatten. If too little is applied, the layer won't spread or bind evenly. The candy makers apply the syrup in short bursts, followed by a drying cycle. To dry each layer, warm dehumidified air is pumped into the pan, either through ducts that lead directly into the chamber or through perforated side vents that circulate around the rotating drum. Each coating cycle, spray, tumble, dry, adds only a fraction of a millimeter of mass to each piece. The factory repeats this cycle dozens of times, building up the candy shells layer by layer until the particles reach their desired diameter. Because Nerds aren't smooth or spherical, but instead irregular and jagged, the motion of the pan is calibrated to encourage slightly chaotic collisions. This helps preserve the rough texture and prevents the shells from polishing themselves into uniform spheres. It's a balance of engineering and deliberate imperfection. Once the pieces reach mid-size, flavoring is introduced. The flavoring agent, usually a concentrated blend of acids, natural or artificial flavors, and a small amount of binding sugar, is mixed into the syrup and sprayed as a component of the next several layers. The inclusion of citric, malic or tartaric acid in these syrups is what gives Nerds their intense tanginess. The acids aren't just flavor additives, they also influence the syrup's drying behavior, and they react slightly with the sugar during curing, adding complexity to the texture and finish. Each flavor batch is kept isolated in its own production cycle. For example, the grape batch and the strawberry batch are never made in the same pan at the same time. Color is added as part of the flavoring syrup or in a dedicated later cycle. High-intensity food-grade dyes are introduced in micro quantities and bond to the exterior of each piece during the drying process. The rotating motion ensures even color coverage across all pieces. If needed, a polishing agent like carnauba wax is added at the end to give the pieces a slight gloss and improve pourability and packaging flow, but unlike smoother candies, Nerds are not excessively polished. Their irregularity is part of their design, and over-polishing would compromise the tactile crunch consumers expect. Once the candies have completed their panning and drying sequence, they are transferred via air ride conveyors or vibratory chutes into sieving units that sort them by size and shape. Undersized particles or pieces fused during the coating process are separated and removed. These may be reprocessed, used in bulk product, or discarded depending on their condition. The main batch continues into temporary holding bins, which act as buffers between panning and packaging. These bins are kept sealed, dry, and mildly climate controlled to prevent any reabsorption of moisture. The packaging process for Nerds is as specialized as the candy itself. Each traditional Nerds box features 2 flavors separated down the middle. This requires a dual hopper system where 2 vibratory feeders, each calibrated for a different flavor, dispense products simultaneously into twin funnels that lead to either side of the box. Boxes are pre-formed from flat stock using a carton erecting machine. The boxes are folded, glued, and printed on site with all product information, flavor names, batch codes, and nutritional data. As the boxes move along the packaging belt, they pass under the dual dispensing nozzles. Each side of the box is filled with exact amounts of its designated flavor, controlled by a combination of weight sensors and timed release gates. Once filled, the box passes through a closing mechanism that folds and seals the top flap, usually with pressure adhesive. After sealing, the boxes are printed with the final production time and batch number using thermal inkjet printers and are diverted to an automated case packing station. Boxes are arranged into cartons using robotic arms that layer them in specific formations designed for stability during transit. Each carton is scanned for completeness, sealed with tape or hot glue, and labeled for inventory tracking. Cartons are palletized in predetermined stacks and shrink-wrapped for storage. Final product pallets are stored in ambient conditions away from direct light and heat sources to preserve color and flavor. Throughout this entire operation, each machine is monitored by an industrial control system that logs key variables such as drum rotation speed, syrup pump flow rate, drying air temperature and humidity, flavoring concentration, and piece weight. If any variable drifts outside its preset tolerance, alarms are triggered, and either adjustments are made automatically or the line is stopped for inspection. In-process quality assurance includes routine sampling of product from each batch. Selected pieces are tested for moisture content using Carl Fisher titration, checked for weight uniformity, color intensity via spectrophotometers, and hardness via compression testing. Flavor strength is assessed by trained sensory panelists who taste test small samples for tanginess, sweetness, and balance. Batches that don't meet standards are flagged for rework or disposal. Samples are retained from every lot in a traceability vault where they're stored for months in case of consumer inquiry or recall verification. Sanitation of equipment between flavor runs is critical. The panning pans are flushed with warm water, scrubbed manually or by automated spray heads, and dried thoroughly. Transfer lines and feed hoppers are vacuumed, wiped, and swabbed for allergen residue, particularly if fruit flavors alternate with sour or spicy variants. All cleaning is verified using protein or ATP tests before a new flavor run can begin. Because nerds have such intense color and acidity, even a tiny bit of cross-contamination could discolor or distort the taste of a new batch. Production lines can be scaled depending on volume requirements. For seasonal or limited edition batches, smaller coating pans and micro-dispensing stations are used. For high-volume standard runs, like grape and strawberry, multiple pans operate in parallel with synchronized drying and transfer systems, feeding a centralized packaging hub. This modularity allows the factory to adapt batch sizes without compromising efficiency. Unlike other panned candies that are polished to a near mirror-like finish, nerds maintain their chaotic and crystallized texture because the syrup formulations are designed to dry unevenly, creating edges and ridges that catch the tongue and amplify the sensory crunch. The layers aren't perfectly smooth and are never compressed, only dried and allowed to harden naturally. This gives the candy its unique tactile appeal. Skittles begin with the creation of their chewy interior core, which is essentially a sugar-based gel formulated for elasticity, density, and controlled chewiness. This core mass is created in large stainless steel cooking vessels equipped with steam jackets that allow precise temperature control during the preparation of the base. The basic ingredients, granulated sugar, corn syrup, and water, are measured automatically by weight sensors and pumped into the vessel, where they're heated while constantly agitated to prevent scorching or uneven caramelization. The temperature is carefully elevated to dissolve the sugar fully and initiate a Maillard reaction-free blend, ensuring that the final texture remains pale and neutral, ready to absorb added color and flavor later. As the syrup cooks, continuous stirrers move through the mix to keep solids suspended evenly. The goal is a thick, clear candy gel that can be cast into molds while retaining its shape and resilience. Once the mass reaches its target viscosity and concentration, it is cooled slightly and pumped through heated pipes to a flavoring station. There, rotating blending heads introduce pre-measured amounts of flavor oils and acid blends to create each Skittles flavor: strawberry, orange, grape, lemon, green apple, and others, depending on the mix. The flavoring is added while the base remains hot to allow complete integration, but cool enough to avoid evaporating volatile components. The flavored mass is divided into color-coded batches, each handled separately. From here, the hot candy is portioned into small droplets using a starch molding system. Large trays of dry cornstarch are stamped with shallow cavities using custom metal boards shaped to the exact dimensions of a Skittle interior. As the trays move along a belt, a depositor head above the line releases precise amounts of the hot syrup into each starch pocket, forming hundreds of raw candy centers per tray. The starch absorbs surface moisture and provides a non-stick bed for the candy to set. Once filled, trays are stacked into large drying tunnels where they are left undisturbed for up to 2 full days. Warm, low humidity air flows through the chambers in controlled patterns, drawing out moisture from the centers gradually to preserve their elasticity while building up a denser outer layer. This results in a finished center that is soft but firm enough to retain its shape under mechanical stress later in the process. After curing, the trays are fed into a starch removal system. High-powered air blowers, rotating brushes, and vibrating sifters remove residual starch from every piece. The clean centers are now semi-finished candies, chewy tablets without any shell or color. They're separated by flavor batch and transferred via inclined vibrating conveyors into large stainless steel holding hoppers, where they're prepared for the shell building stage that gives Skittles their iconic look and texture. The next phase is sugar shelling, or panning. This process takes place in large rotating pans, angled drums fitted with smooth interiors that allow candy pieces to roll and tumble freely without becoming damaged. Each pan is dedicated to a single flavor to avoid cross-contamination. Thousands of centers are loaded into each pan, which slowly rotates on its axis, creating constant motion across the mass. A fine spray of sugar syrup, made from a blend of sucrose, glucose, and water, is gently misted over the tumbling centers via precision nozzles. Immediately after each spray, dry sugar is dropped into the pan to bind to the surface of the syrup. A blast of warm, dehumidified air is pumped into the chamber to dry the layer instantly. This process, syrup, sugar, drying, is repeated dozens of times over several hours. Each application adds a microscopically thin layer of sugar to the surface of every candy, gradually building up the hard, crunchy shell that surrounds the chewy interior. The tumbling motion ensures even coverage and encourages the natural formation of slightly curved, asymmetric shapes that Skittles are known for. Unlike perfectly round candies, Skittles are meant to have slight natural variation, which enhances their sensory appeal when poured, handled, and chewed. Once the base white shell has been built, colorants are added in the final layers. These colors, vibrant purples, reds, oranges, yellows, and greens, are mixed into a final set of sugar syrups and applied using the same spray and dry sequence, but in tighter, faster rotations to lock in the color before it runs or pools. This layering technique allows for deep color saturation without creating thick outer shells. Each color batch is processed separately, and equipment is cleaned between runs to prevent color bleeding or flavor confusion. After the last color layer is applied and dried, the candies move to a polishing pan. A small amount of carnauba wax or a food-grade polishing glaze is misted over the rotating candies, which are tumbled slowly in low-heat conditions to spread the glaze evenly. This produces the glossy finish Skittles are known for and improves the handling and flow of the product during packaging. The wax coating also acts as a moisture barrier, extending shelf life and preventing stickiness in humid environments. At this stage, Skittles are visually complete but not yet branded. For that, the candies are sent to a high-speed printing line. The signature S logo is printed onto each piece using edible white ink, delivered by specialized inkjet heads that can stamp thousands of pieces per minute. The candies move under the printer on narrow tracks that separate them just enough to expose the surface. Sensors detect orientation and adjust the print head as needed to ensure the S is centered on each piece. After printing, the candies are allowed to rest briefly in shallow bins to allow the ink to fully dry and bond to the shell. Once dry, all colors are recombined into a multi-flavor blend by feeding them into a wide mixing chute where precise volumes of each flavor are blended according to recipe. Sensors verify that the correct ratios are being maintained, and camera systems ensure color consistency throughout the mix. Blended candies now move to the packaging stage. Skittles are offered in various sizes, from single-serve pouches to large resealable bags and novelty containers. Each format has its own automated line. All begin with a multi-head weigher, a machine that uses a series of load cells to determine the exact amount of candy to release into each package. Dozens of weigh hoppers are filled and recalibrated multiple times per second to ensure that each pouch receives a consistent net weight. The weighed candies fall through chutes into form-fill seal machines that create bags from roll stock film. This film is unwound, shaped into a tube around a filling nozzle, and heat sealed at the bottom to create a pouch. The candy drops in immediately after, and a top seal is applied, finishing the package. A notch is cut for easy opening, and in resealable formats, a zipper or adhesive strip is pressed into the film just before the top seal. Each sealed pouch is printed with a production date, expiration date, and batch number using thermal or laser printing units. They then pass through metal detectors and X-ray scanners to ensure no foreign objects are present. Any pouch that fails the inspection is automatically ejected from the line. Verified packages are moved onto robotic palletizers, where they are sorted into boxes or cartons depending on shipping format. The cartons are sealed, stacked on pallets, and stretch wrapped for shipping. Some pallets are routed directly to distribution centers, while others are stored in warehouse inventory. The warehouse conditions are temperature and humidity controlled to preserve the integrity of the sugar shells and to prevent color fading or moisture pickup. At every stage of this process, from syrup cooking to final packaging, data is recorded and tracked in a central control system. This includes temperatures, weights, drum speeds, spray times, drying durations, color intensity scores, and batch traceability markers. Each component is monitored to prevent deviation, and any anomaly, whether in syrup viscosity or final product gloss, is flagged by the system and reviewed by technicians. Sanitization between batches is managed using clean-in-place systems for pipes and tanks, and full manual cleaning for tumblers, dryers, and packaging stations. After each run, pans are emptied, washed with heated water, sprayed with food-safe detergents, and dried using forced air. Color stations are scrubbed thoroughly to prevent cross-contamination, particularly between flavors that use sensitive dyes or volatile oils. M&Ms begin with the core of the product, milk chocolate that must be formulated, tempered, and molded into small lentil-shaped pieces before the colorful candy shells can be applied. The chocolate is produced in dedicated chocolate-making facilities that start with cocoa liquor, cocoa butter, sugar, milk powder, and emulsifiers, all of which are carefully metered and blended together in high-capacity mixers. The cocoa liquor itself is prepared by grinding roasted, winnowed cocoa nibs into a thick paste. This paste, rich in both cocoa solids and fat, is mixed with sugar and milk solids to form the base of milk chocolate. The mixture passes through a series of refining rollers to reduce the particle size to under 20 microns. This critical threshold ensures that the final chocolate has a smooth, creamy texture when consumed. Once refined, the mix enters large conching machines, heated steel vessels with rotating arms that knead the chocolate slowly for hours, evaporating unwanted acids, enhancing flavor, and encouraging even distribution of the cocoa butter across all particles. This process can last for 6 to 24 hours, depending on the desired flavor profile and chocolate texture. After conching, the chocolate is tempered. This process uses carefully controlled heating and cooling cycles to stabilize the cocoa butter crystals into the correct polymorphic form, known as Form 5, which provides the finished chocolate with its signature glossy appearance, firm snap, and resistance to blooming. The tempered chocolate is now ready to be molded into the M&M centers. To create the core shapes, the chocolate is deposited into rotary molding drums. These are chilled stainless steel or polycarbonate molds arranged on a wheel or carousel system. As the tempered chocolate is portioned out by depositor heads, it fills lentil-shaped cavities with exact mass. The molds rotate through a refrigerated chamber that cools the chocolate evenly from all sides, causing it to solidify into firm, smooth discs. Once cooled, the chocolate pieces are demolded and released onto conveyors. From here, the molded chocolate centers are sent into a conditioning tunnel where they are stabilized at a consistent ambient temperature to equalize internal stresses and prepare the surface for coating. The now solid chocolate lentils are poured into large revolving coating pans, which are the heart of the shell application process. Each pan is a large, angled, spinning drum where the pieces tumble continuously in a gentle motion. In these pans, the sugar shells are applied through a process called hard panning. The panning process begins with the application of sugar syrup, a concentrated solution of sucrose, glucose, and water. Nozzles spray the syrup onto the tumbling chocolate pieces in timed bursts, ensuring a very thin, even coating across all surfaces. After each syrup application, dry powdered sugar is introduced, to absorb the moisture and initiate crystallization. Warm, dry air is blown into the pans to dry the coating quickly. This spray-dry cycle is repeated many times, gradually building up the hard, crunchy shell around the chocolate core. Each layer adds just a fraction of a millimeter to the total size, so dozens of layers are required to reach the final shell thickness. The tumbling motion ensures even coverage while preventing the candies from clumping or sticking together. Operators carefully monitor syrup flow rate, pan speed, and air temperature to maintain consistency across millions of individual pieces. If too much syrup is applied at once, it can cause pooling, lopsided shells, or color unevenness later in the process. Once the desired shell thickness is reached, coloring begins. Food-grade dyes specific to each M&M color, red, yellow, blue, green, brown, and orange, are introduced as part of a final sugar coating stage. The dyes are added either directly to the syrup or sprayed separately between final sugar layers to lock in the color. The timing of color application is crucial. It must occur after the shell has enough structure to support liquid application, but before final drying and polishing. Each color batch is processed separately to prevent crossover. Once the color has dried and bonded to the outer sugar layer, the pieces move to the polishing stage. A polishing solution, often containing carnauba wax or a similar food-safe glaze, is applied in small amounts to the candy while it tumbles in polishing pans. The motion smooths out any residual roughness and creates a glossy, hard finish that resists moisture and improves shelf life. The polishing process also ensures that the M&Ms have the signature reflective sheen that sets them apart from dull-coated products. After polishing, the candy is allowed to cool and set. Batches of each color are stored in temporary silos or bins where they're held under controlled temperature and humidity to stabilize the shells before printing. Printing is handled by high-speed rotary inkjet printers that stamp a white M onto each piece. The candies move on wide, vibrating conveyors, passing under print heads that are aligned to detect the center of each candy and apply the M with precision timing. The printing ink is edible, fast-drying, and specially formulated to bond with the candy shell without smudging or rubbing off during packaging. To ensure complete coverage, each printer is synchronized to hit the top face of the lentil shape, which is tracked using cameras or mechanical positioning sensors. The result is consistent logo placement with minimal rejection rates, even at speeds of tens of thousands of pieces per minute. After printing, the candies are ready to be mixed. M&Ms are known for their assorted colors, so dedicated blending machines are used to combine exact proportions of each color into a consistent mix. Color metering chutes control how much of each shade enters the final stream, and photosensors validate that the blend meets the target ratio. The mixed candies then move to the packaging line. The packaging phase varies depending on product format. Individual servings, sharing bags, and bulk formats each require different equipment. At the start of this phase, multi-head weighers measure precise amounts of product using multiple load cells arranged in combination patterns. These weighers can make rapid decisions to select the best combination of hoppers that add up to the target weight, often accurate to within 1/10 of a gram. Once weighed, the candies fall into vertical form-fill seal machines that form a pouch from flat plastic film, seal the bottom, release the candy, then seal the top and apply a tier notch. For rigid containers, like tubes or cartons, robotic arms deposit the candy into pre-formed packaging before sealing with foil, plastic lids, or induction seals. Each pack is printed with production codes, expiration dates, and batch numbers for traceability. Filled packs pass through quality control stations that include metal detectors and X-ray scanners to ensure no foreign materials are present. Sealed bags are checked for leaks using pressure tests and often weighed again to confirm accuracy. Packs that pass are grouped into cartons using robotic case packers labeled, and palletized. Pallets are shrink-wrapped and stored in temperature-controlled warehouses to prevent shell degradation or fat bloom on the chocolate core. Throughout this process, data from every step is captured in the factory's SCADA system. Operators track temperature profiles during chocolate tempering, monitor panning duration, shell thickness, syrup concentration, and dye ratios. Real-time analytics allow for micro-adjustments to maintain consistency across thousands of kilograms of candy produced per day. Sanitation procedures are also highly standardized. All equipment is made from food-grade stainless steel and is disassembled or flushed between batches. Water lines and syrup pumps are cleaned with detergent cycles, and pans are scrubbed and visually inspected before reuse. Flavor or color transitions require dedicated cleaning cycles to avoid trace contamination, especially when switching between seasonal colors or limited edition batches. Lollipop production begins with dry granulated sugar and glucose syrup, delivered in bulk into silos and heated stainless steel storage tanks. The sugar is conveyed through screw feeders into a large dissolving vessel. Simultaneously, glucose syrup is pumped through jacketed pipelines to the same vessel. Water is introduced at a controlled rate to create the initial slurry. The temperature is raised to approximately 110 degrees, while agitators rotate to dissolve all solids. The mixture becomes a clear, homogeneous sugar solution. Once the sugar is fully dissolved, the syrup is transferred via gravity or pump into a vacuum batch cooker or a continuous candy cooker. The cooker raises the syrup's temperature to 145 degrees to 150 degrees while lowering the internal pressure. The reduced pressure allows water to boil off rapidly without degrading the sugars. The syrup thickens into a dense, high brix mass. Sensors monitor real-time concentration and adjust heat and vacuum accordingly to maintain the target range, typically 98-99% solids. The cooked candy mass exits the vacuum chamber through a heated outlet, either dropping onto a stainless steel cooling table or into a rotary kneading kettle. On the cooling table, scraper arms fold the mass over itself as it cools. Inside the kettle, mixing paddles rotate at set intervals. The temperature drops gradually to about 90 degree cooks. At this stage, flavor oils, acids, colorants, and emulsifiers are added. Dosing pumps inject precise volumes of ingredients based on the batch weight. Mixing paddles distribute the additives evenly throughout the mass while avoiding air entrapment. If a layered or dual-color lollipop is being produced, the candy batch is divided into separate portions. Each portion is flavored and colored independently in separate kettles. A heating jacket maintains each portion at a stable working temperature. When ready, the portions are loaded into a batch former that can extrude them side by side or swirl them together during the rope formation process. Once mixing is complete, the candy is transferred to a rope sizer. The mass is fed into the machine and drawn through a series of sizing rollers that reduce and elongate the bulk mass into a continuous rope of uniform diameter. Each roller pair incrementally reduces the thickness while maintaining roundness. Servo-driven rollers and load cells ensure tension remains steady along the entire length. Inline cameras monitor the rope diameter within plus 0.5 mm tolerance. As the rope advances, it enters the forming section. Here, it is pulled into a rotary die forming machine. This system consists of two steel rollers with precision-cut cavities. As the rope enters the nip point, a stick is inserted from below by a mechanical arm into the soft mass at the exact moment of compression. The die cavities close, shearing the candy rope and forming the lollipop head around the stick simultaneously. Sticks are fed from a vertical hopper onto a horizontal conveyor where they are spaced using star wheels. They travel into the insertion mechanism where grippers or push rods insert them directly into the hot candy as it is formed. The insertion depth, pressure, and angle are all adjustable. Any stick not aligned properly is automatically rejected before contact with the product. After forming, lollipops drop onto a cooling conveyor. The system is divided into zones with progressively lower air temperatures, beginning at around 25 degrees Celsius and dropping to 10 degrees C. Air is circulated through HEPA filters to remove particulates and maintain constant humidity. Cooling takes 5 to 8 minutes, depending on candy size and formulation. The sticks are kept horizontal to prevent gravitational deformation of the still soft candy head. Once fully cooled and hardened, the lollipops enter the wrapping stage. Multiple high-speed wrapping machines operate in parallel. Each machine feeds film from a large roll. Photocells track registration marks to ensure proper logo alignment. Film is cut into pre-sized sheets and fed into the wrapping jaws. Lollipops arrive single file via guide rails and timing screws. As each piece enters the wrapping section, it is met with a film sheet. The candy is centered on the wrapper, and the machine either twist wraps the film at both ends or folds it around the head and seals it with heated jaws and pressure rollers, depending on the wrap style. Speeds reach up to 800 lollipops per minute per machine. Sensors verify the presence of each stick and confirm film seal integrity. If a lollipop is missing a stick, misaligned, or improperly sealed, it is rejected via an air blast or servo diverter. Properly wrapped lollipops are conveyed to a grouping area where they are accumulated for final packaging. Packaging varies depending on format. Some lollipops are bagged in high-speed, vertical form-fill seal machines. The wrapped candies drop into vibratory feeders that portion them into buckets. Buckets empty into a forming tube where plastic film is formed into a bag, filled, and sealed on the top and bottom. Sealing jaws cut and compress the film simultaneously, producing a finished pouch. For tray packs, lollipops are grouped into clusters using a belt divider. Robotic arms or pushers load fixed quantities into cardboard trays or blister packs. Cartoning machines erect the trays, insert the product, and apply hot melt adhesive to seal the cartons shut. Inkjet or laser printers mark each pack with batch codes and expiration dates. Cartons flow to a case packer, where they are grouped and packed into master cartons. Mechanical arms fold the outer box and glue or tape the flaps. These boxes are stacked in layers on pallets by robotic palletizers. The system alternates stack orientation by layer for load stability. Slip sheets are inserted between layers by a vacuum picker. When the pallet is complete, it transfers to a stretch wrapper. A rotating arm or turntable applies a pre-stretched plastic film around the pallet. Wrapping parameters are adjusted based on pallet height, product weight, and load configuration. Once wrapped, each pallet receives a barcode label and is conveyed to the shipping dock. All stages of lollipop production are managed by programmable logic controllers. Every machine, cookers, rope sizers, forming presses, stick inserters, wrappers, and palletizers is integrated into a plant-wide SCADA system. Operators monitor real-time metrics, including syrup concentration, rope tension, cutter timing, seal temperature, stick depth, wrapping accuracy, packaging speed, and output count. Cooking systems are equipped with conductivity probes and pressure sensors. These devices ensure consistent cooking profiles by regulating steam pressure, vacuum levels, and temperature. Flow meters control syrup and water ratios during dissolving. In the cooling tunnel, temperature and humidity sensors maintain conditions within tight limits to avoid surface cracks or bloom on the hardened candy. Line synchronization is maintained through encoder feedback. Rope feed rate, die rotation, and stick timing are adjusted in real time to prevent drift or misalignment. High-speed cameras inspect each lollipop post-forming for symmetry, stick centering, and surface quality. A quality control logic system tracks defect rates and triggers maintenance if thresholds are exceeded. For striped lollipops, colored candy masses are co-extruded through a color stacking head before entering the rope sizer. Stripes are achieved by arranging differently colored masses side by side or spiraling them with twist control. Layer geometry is controlled by adjusting feed angles and rotation during rope pulling. Dual flavor or filled lollipops use concentric forming. An inner core, often a soft center or powdered flavor pocket, is co-deposited during the forming process. Dual extruders feed the core and shell simultaneously through concentric nozzles. The rope is cut and shaped with the filling encased completely inside. Production speed depends on format. A single forming line can produce over 1,000 lollipops per minute. With multiple lines operating simultaneously, output scales into the millions per day. Each system runs continuously with minimal downtime. Quick release tooling and automated cleaning reduce changeover time between flavors or shapes. Cleaning in place systems are installed on all cooking, mixing, and delivery equipment. These cycles run automatically between batches. Hot water flushes remove residual candy. Caustic detergent circulates through tanks, pumps, and piping. A final rinse ensures all surfaces are food safe. The cleaning process is monitored by conductivity sensors and logged by the control system. Sticks are produced off-site to specification and delivered in bulk. Materials range from extruded polystyrene to compressed paper. Before entering the line, sticks pass through a stick inspector with vision sensors to check for length, roundness, and cleanliness. Only compliant sticks are fed into the press. Any deviation beyond plus 0.5 mm in length or 1 gralus of bend results in rejection. Muffin production in a factory begins with the precision handling of core ingredients: wheat flour, granulated sugar, vegetable oil, eggs or egg replacer, milk or whey solids, water, leavening agents, salt, emulsifiers, and flavor additives. All dry materials arrive in super sacks or silo-fed bulk containers. Liquids are delivered in food-grade tankers and pumped directly into insulated holding tanks. Ingredient feeding systems are automated with load cell-equipped silos, volumetric dosing hoppers, and inline mass flow meters that measure and control exact quantities in real time. The mixing process starts in a large-scale planetary or horizontal mixer. Flour is fed from silos through enclosed pneumatic lines. Sugar is metered in by screw feeders. Liquid components, including water, oils, eggs, and emulsifiers, are introduced from jacketed tanks through pressurized dosing pumps. The mixer uses high-torque arms or paddles to fold the batter, and a PLC-based control system sequences ingredient additions based on a time and speed program. Sensors monitor viscosity, temperature, and mixing torque to determine completion. The mixing cycle is designed to develop a consistent batter texture while minimizing gluten overdevelopment. Most muffins use the muffin method, where liquids and dries are blended quickly with minimal agitation. The final batter is thick, glossy, and aerated. Scraper blades clean the sidewalls of the mixing bowl continuously to ensure uniformity throughout the mix. Once mixing is complete, the batter is pumped into an intermediate holding hopper. These hoppers are jacketed to maintain temperature, typically between 18 degrees Celsius and 26 degrees Celsius, and feature slow-speed agitators to prevent separation. The batter is held under light pressure to feed the depositors efficiently and without introducing excess air. Meanwhile, paper muffin cups are dispensed into baking trays by a cup denister. Trays are made from perforated metal or non-stick coated aluminum, often holding 12 to 24 cavities per tray. The trays travel along a conveyor system toward the depositing zone. As each tray enters the depositor station, it is precisely indexed into place by servo-controlled gates. Batter is deposited using multi-nozzle volumetric piston depositors. These depositors operate with individual cylinders that draw and dispense set volumes of batter into each cup. Fill weights are carefully calibrated, typically between 50 and 120 grams per muffin, depending on product specifications. Tolerances are within +/- 1.5 grams. Deposit profiles can be circular, spiral, or domed, depending on desired peak structure. Depositor heads are adjustable in height and spacing, allowing format changes without complete tooling replacement. For muffins with inclusions, such as blueberries, chocolate chips, or nuts, an ingredient dosing unit integrates with the depositor. Inclusions are metered into the batter just before deposition to prevent sinking or damage during mixing. The distribution system uses augers or vibration channels to deliver equal portions into each cup, either layered or blended depending on recipe. Optional toppings are applied at this stage. Streusel, sugar crystals, seeds, or flavored crumbles are dropped by overhead sprinklers or belt feeders. These systems are synchronized with tray motion, using vision sensors to detect cup position and deliver toppings directly onto the surface of each batter portion. Filled trays proceed to the oven. Industrial tunnel ovens, either gas-fired or electric, bake muffins continuously. The oven conveyor moves at a speed determined by product size and bake profile, typically yielding a dwell time of 12 to 18 minutes. Oven zones are independently controlled for top and bottom heat, with precise air circulation to ensure even baking. Core product temperature is monitored using inline thermocouples that pierce random samples. Exit temperature targets typically range from 93 degrees Cs to 98 degrees Cs. Inside the oven, batter rises due to the activation of chemical leavening agents. Steam forms from the water and egg content, expanding air cells and lifting the batter upward. As proteins coagulate and starches gelatinize, the muffin structure is set. Surface coloration and crust formation are controlled by air humidity and sugar content. Once baked, trays exit the oven onto a cooling conveyor. This conveyor is long enough to allow the muffins to cool from above 90 degrees Celsius down to ambient room temperature, usually within 20 to 30 minutes. High volume air blowers accelerate heat dissipation. Muffins remain in their trays during this time to retain shape and prevent sticking to belts. After cooling, muffins are depanned. A pneumatic or mechanical depanner inverts the tray and applies a brief vacuum or finger push to lift each muffin out. The muffin cups remain intact, and the products are transferred onto a belt for inspection. Empty trays are returned via overhead conveyors or underbelt returns to the cup denesting station for reuse. Muffins are now inspected by a vision system. Cameras mounted above and to the side scan each muffin for volume, surface cracks, peak height, and alignment in the paper cup. Any product that falls outside the specification window is diverted by a mechanical pusher or drop gate. Approved muffins continue to the packaging zone. Packaging formats vary depending on customer needs. Muffins can be individually wrapped, packed in clamshell trays, or sealed into multi-packs. For individual wrapping, muffins are fed into a flow wrapping line. Each muffin enters a forming collar, where film is wrapped around it and sealed using heated rotary crimpers. Longitudinal and cross seals are made with controlled temperature and pressure. Speeds can reach up to 300 muffins per minute per line. For clamshell packing, muffins are guided into a colada, where robotic pick and place arms grip each unit and place it into thermoformed PT trays. These trays are then lidded and sealed with tamper-evident films or snap-on covers. Date and batch codes are printed using thermal inkjet printers. For bulk or food service formats, muffins are loaded into cardboard display trays or placed directly into polyethylene-lined cartons. Cartons are erected from flat blanks using a box erector. Muffins are loaded in rows, either manually assisted or robotically, and the carton is then closed with hot melt adhesive and conveyed toward the palletizer. At the palletizing station, robotic arms equipped with vacuum grippers or mechanical forks stack cartons onto wooden or plastic pallets. Patterns are selected based on case size and distribution route. Slip sheets are inserted every few layers for stability. Finished pallets are stretch wrapped by a rotating arm system and labeled with barcodes and shipping data. All production steps are integrated into a plant-wide control system. Programmable logic controllers coordinate each machine, while SCADA systems provide real-time data on batch progress, line speed, machine temperature, deposit weight, oven humidity, and output count. Operators monitor the entire line from centralized terminals, adjusting set points and diagnosing faults without stopping the process. Ingredient traceability is managed through automated lot tracking. Each ingredient batch is scanned upon entry and linked digitally to every production batch. Finished goods are barcoded and traced back through mixing, depositing, and baking history. If a deviation occurs, the system flags affected pallets and isolates them immediately. Cleaning is performed through a mix of clean in place and clean out of place protocols. Mixing tanks, pipes, depositors, and pump systems are flushed with alkaline detergent followed by a hot water rinse. Baking trays and conveyors are cleaned with steam or dry brushing. Nozzle heads and sensor lenses are wiped with food-safe solvent solutions. Environmental conditions are tightly controlled. The mixing room is temperature stabilized to avoid batter inconsistency. The depositing area uses filtered air to keep particles off open trays. Oven exhaust is captured and scrubbed. Packaging areas are overpressurized with filtered air to minimize dust entry. Air knives and vacuum hoods remove crumbs during transfer points. If muffins are frozen, post-production, they are conveyed directly into a spiral freezer. Cold air at 35 degrees Celsius rapidly reduces product temperature to below 18 degrees Celsius within 30 minutes. Frozen muffins are then flow wrapped or shrink wrapped in bulk, palletized, and moved into cold storage. The entire process is timed to avoid moisture condensation and surface bloom. Shape consistency is enforced at multiple stages. During depositing, laser sensors measure batter height. Post-baking, peak height and crown diameter are scanned optically. Deformed or underfilled units are rejected before reaching packaging. Automated systems collect real-time statistics to maintain statistical process control. The production line is modular. Deposit heads, paper cup sizes, and topping applicators can be changed within minutes. Oven belts, mixing times, and wrap formats are selected through the control interface. Recipe memory allows for instant switchovers without manual recalibration. Muffin factories operate continuously, running multiple shifts with minimal stoppages. High-volume lines produce tens of thousands of muffins per hour. Every unit is created through thermal transformation, timed chemistry, pneumatic forming, and servo-synchronized packaging. Every process step is calibrated, controlled, and monitored to meet exact physical and sensory specifications. The factory production of chocolate chip cookies begins with the bulk delivery of essential raw ingredients. These include wheat flour, white and brown sugars, vegetable shortening or butter substitute, liquid eggs or pasteurized egg products, chocolate chips, leavening agents, salt, emulsifiers, water, and flavorings such as vanilla. Dry ingredients like flour and sugar arrive in super sacks or silo containers and are transferred pneumatically or via screw conveyors into batching silos. Liquid ingredients are stored in temperature-controlled stainless steel tanks connected to dosing lines. Chocolate chips are stored in insulated bins and gently agitated to prevent compaction or melting. Automated ingredient handling systems prepare each batch according to a programmed recipe. The process begins in the scaling room or dosing station, where load cells measure and release precise amounts of dry and wet ingredients into transport hoppers. Materials are conveyed into a high-capacity horizontal mixer, typically of the ribbon or paddle variety. These mixers are equipped with dual-axis blades and variable speed motors. Ingredients are added in a fixed sequence. Fats and sugars first to cream, then eggs and water, followed by dry powders, and finally chocolate chips. Mixing proceeds through defined phases. During the creaming phase, sugar granules break down the fat, creating air pockets essential for cookie spread and tenderness. The incorporation of eggs and water creates an emulsion that stabilizes the dough. As flour and leavening agents are added, the blades slow down to avoid overdevelopment of gluten. The chocolate chips are added last and folded gently to prevent breakage. Inline torque sensors monitor dough consistency, and viscosity meters verify proper development. Batch temperatures are maintained between 18 degrees Celsius and 24 degrees Celsius to prevent fat melt and preserve dough structure. Once mixed, the dough is transferred into a hopper positioned above the forming line. Dough moves via auger or vacuum feed into a volumetric portioning system. A rotary cutter or wire cut depositor divides the dough into individual pieces, each weighing between 25 and 50 grams, depending on the product specification. The depositor uses servo-driven pistons to extrude dough pieces onto a moving steel mesh or Teflon-coated band conveyor. Optical sensors monitor spacing, alignment, and shape, correcting for drift in real time. For wire-cut lines, dough is pushed through nozzles and sliced cleanly by a fast-moving wire as the band advances. For rotary molded formats, dough is pressed into engraved molds on a rotating drum, then released onto the band using a flexible scraper blade. Shape, weight, and chip distribution are confirmed by an overhead vision inspection system using laser profiling and high-speed imaging. Defective pieces are automatically rejected via air puffs or diverter gates. Decorative or functional toppings, such as extra chocolate chips, coarse sugar, or sea salt, can be added before baking. These are applied using vibratory feeders or pneumatic dispensers, synchronized with the conveyor speed. Toppings are placed with positional accuracy, controlled by encoder feedback. The unbaked cookies enter the oven on a continuous conveyor. Most large-scale bakeries use tunnel ovens ranging from 25 to 60 meters in length. Ovens may be gas-fired, electric, or hybrid, and are divided into multiple heating zones. Each zone has independently controlled top and bottom heating elements, recirculating fans, and steam injection systems. Bake times range from 6 to 12 minutes, depending on cookie size, dough moisture, and desired texture. As cookies pass through the oven, heat activates the leavening agents, causing the dough to expand. Water turns to steam, fats melt, and proteins begin to coagulate. Sugars caramelize on the surface, contributing to flavor and browning. Top heat ensures color formation, while bottom heat ensures base firmness. An inline thermal imaging system monitors surface temperature and identifies any uneven baking. Oven humidity is also regulated to manage cookie moisture and bite texture. After baking, cookies exit the oven at internal temperatures above 90 degrees and quarks. They are transferred to a multi-tiered cooling conveyor that spans 20 to 40 meters in length. Cool ambient air is blown across the surface of the cookies to gradually reduce their temperature to 30 degrees or lower. The cooling line uses stainless steel or open mesh plastic belts to allow airflow from above and below. Rapid cooling is avoided to prevent cracking or structural collapse. Crumb blowers and air knives remove any loose particles generated during baking. Once cooled, cookies pass through a final inspection station. A high-speed vision system checks each unit for diameter, thickness, browning level, chip exposure, and edge uniformity. Any cookie failing the inspection parameters is ejected automatically. Passing cookies proceed to the packaging section. Depending on the final format, cookies may be packed in flow wrap, trays, clamshells, or flexible pouches. For flow wrap, cookies are aligned single file by a lane guide and transferred onto film. Film is unwound from a roll, cut to length, and wrapped around each cookie. Heat sealing jaws close the ends and form a longitudinal seam. Wrapping speeds can exceed 500 cookies per minute per lane. For tray packing, cookies are collated into rows by a bucket conveyor and placed into pre-formed plastic or paperboard trays by robotic pickers. In multi-pack formats, cookies are stacked vertically or nested side by side using servo-driven stackers. These stacks are inserted into pouches or boxes that are formed, filled, and sealed in a continuous motion machine. Machines apply nitrogen flush to pouches before sealing to displace oxygen and extend shelf life. Date codes and batch numbers are applied using thermal inkjet printers or laser coders. Barcodes are printed for inventory and traceability. Wrapped products are collated into cartons by robotic arms equipped with suction grippers. Cartons are sealed with hot melt glue and stacked onto pallets in pre-programmed patterns. Palletizers use multi-axis robots with slip sheet dispensers to build stable, shippable loads. Pallets are conveyed to a stretch wrapper where they are secured with plastic film. Labels with tracking codes and distribution information are applied before pallets are moved to dispatch or cold storage. All stages of production are monitored and controlled by a centralized PLC-based automation system. The entire factory line is integrated through SCADA interfaces that provide operators with real-time dashboards showing mixer status, dough temperature, line speed, oven zone profiles, moisture content, wrapping rate, and defect counts. Recipe management software ensures every batch conforms to specification and every change is logged digitally. Clean-in-place systems are used for all dough contact equipment. After production, mixers, hoppers, pipelines, and depositors are flushed with food-safe detergent and rinsed with hot water. Belt surfaces are cleaned with steam or sanitizing solution and scraped with mechanical blades. Oven interiors are brushed and vacuumed between shifts to remove carbonized residue. Environmental conditions like air pressure, temperature, and humidity are tightly controlled in all processing zones to prevent microbial growth and maintain dough stability. Ingredient traceability is maintained through barcode scanning and batch logging. Each input is recorded upon arrival and linked to its corresponding finished batch. If any quality issue is detected downstream, affected products can be isolated immediately through backtracking. Quality assurance teams conduct routine sampling, including water activity, texture, chip dispersion, packaging seal integrity, and shelf life simulations in controlled chambers. Some facilities operate in robing lines for chocolate-dipped or striped cookies. These cookies exit the oven and are passed through a tempering tunnel where they receive a coating of milk, dark, or white chocolate. The coating is applied using cascading curtains or rotating drums, followed by a cooling tunnel with airflow designed to produce a glossy finish and stable crystallization. Other variants include filled cookies, where dough is extruded with a central cavity filled with chocolate paste, caramel, or fruit gel. These are formed using a co-extrusion head that aligns both dough and filling. The filled ropes are cut by guillotine or rotary blades and shaped prior to baking. Additional vision inspection ensures filling is centered and not leaking. Smarties begin with sugar, which arrives in granulated form, stored in sealed stainless steel silos. Sugar is pneumatically transferred to the batching system through enclosed pipes. A fixed quantity of sugar is weighed and transferred to a rotating pan coder, which serves as the initial forming chamber. Inside the pan coder, fine misting nozzles spray a sugar solution to bind dry sugar particles. Centrifugal force distributes the syrup across the pan surface, while rotation builds uniform cores. These rotating pans are tilted slightly forward and spin at a constant rate to ensure layering occurs evenly on all particles. Each pass adds mass to the sugar cores, which slowly grow into uniform spheres. The syrup concentration is adjusted by flow meters to maintain proper adhesion without overcoating. Once the cores reach target size, they are dried using dehumidified air blown from a ring manifold mounted inside the pan. The dried sugar cores are sieved using vibratory screens to separate non-uniform particles. Undersized or misshaped cores are removed and recycled through a remelt system. Only cores within strict diameter tolerance proceed to the coating line. The selected cores are transferred by vacuum conveyor to the color coding pans. These pans are also tilted and use internal baffles to create tumbling action. Colored sugar syrup is sprayed onto the rotating cores using precision air-assisted atomizers. Each color batch is processed separately to avoid pigment contamination. The syrup contains food-grade dye and a fixed ratio of glucose to prevent crystallization. The color builds in thin transparent layers with multiple passes. Air jets accelerate, drying between each pass without disturbing coating adhesion. A fixed weight of syrup is applied per kilogram of product to ensure consistent color intensity. Optical sensors monitor surface reflectivity to detect coating completeness. Each pan batch continues until desired hue and opacity are reached. After coloring, the coated Smarties move to a polishing stage where they are treated with a food-grade wax solution. This step is done in smaller polishing pans with a lower tilt angle and slower rotation. A fine mist of carnauba wax is sprayed using atomizing nozzles to create a thin surface layer. Polishing lasts 5 to 8 minutes, depending on batch size and wax viscosity. Final gloss level is checked using a reflectometer. Finished pieces are then cooled using ambient airflow and discharged onto an inspection conveyor. The conveyor passes beneath a digital camera array, which checks for shape consistency and surface defects. Air jets remove any pieces outside tolerance. The remaining product enters a vibrating chute that feeds into the printing station. Each Smartie is printed with a white edible ink letter using a rotary pad printer. The printer contains a silicone pad which presses into an ink-filled cliché plate to pick up the letter. The pad then presses onto the candy surface, which conforms slightly to ensure full transfer. Ink drying occurs almost instantly due to ethanol-based solvents. The printed pieces continue on a conveyor to a temporary holding bin. The bin meters product flow into the packaging line, which includes weighing scales and filling hoppers. Weighing scales use load cells to dispense exact net weight quantities into each chute. The chutes feed either roll wrapping machines or blister forming equipment depending on format. For roll packs, Smarties are released onto a continuous wrapper film. Film feeding is driven by a servo motor, which synchronizes with the candy drop. Once the set count is reached, rotary knives cut the film into individual lengths. Heat seal bars close both ends of the film around the product. Roll packs exit the machine and are stacked in cartons. Blister packs are made by forming cavities in thermoplastic film using vacuum and heat. Smarties are dropped into each cavity by a gate dispenser. A foil lid is laminated to the top of the film using a heated roller. Boxed formats involve volumetric fillers, which drop measured product into upright cartons. Cartons are formed from flat blanks using a rotary carton erector. Filled cartons pass through a hot glue sealing station before entering the coding unit. All packaged formats are printed with batch number and timestamp using thermal inkjet printers. Finished units move along conveyors to the collating area, where robotic arms group products into larger cases. Cases are formed by an automatic case erector, which folds and seals flaps using glue. Collated products are pushed into the case and the top is sealed in a separate station. Each case is labeled using a print and apply system that adheres barcodes and contents description. Cases are transferred to palletizers, which stack them onto wooden or plastic pallets using a vacuum gripper arm. Stack height is determined by case weight and stability requirements. Full pallets are stretch wrapped with film before transfer to cold storage. Color production is kept isolated to prevent cross-contamination. Each color is made using dedicated syrup tanks and pump circuits. After each batch, the syrup lines are flushed with hot water, followed by a compressed air purge. Sugar syrup used for coating is heated in double-jacketed tanks with agitation. Temperature is maintained at 110 degrees Celsius for flow and binding properties. Syrup is filtered through a fine mesh screen before entering the coating pan spray system. Atomizing nozzles are adjusted for droplet size using air. Pressure regulators. Smaller droplets create smoother surfaces, while larger droplets increase build-up rate. The nozzle distance from product bed affects coverage radius and drying uniformity. Drying air is conditioned by passing through a desiccant dehumidifier and a preheater. Air temperature and humidity are set based on coating thickness. Flow rate is managed through adjustable louvers at the pan inlet. Pan rotation speed affects rolling frequency and layer adhesion. Faster speed increases agitation but can cause chipping. Slower speed allows better leveling of syrup layers but requires longer cycles. Optimal speed is determined for each pan size and batch load. Letter printing uses ink that contains titanium dioxide for opacity. The cliché plate is laser etched with letter shapes and mounted on a rotary drum. Each pad picks ink from the etched cavity and applies it to a passing candy unit on a timing belt. Positioning is maintained using optical encoders that sync the pad. Strike with the candy location. Missed prints are detected by contrast sensors. These pieces are removed using side air jets directed by the control unit. Packaging materials are fed from rolls mounted on unwind stations. Tension is controlled by dancer arms connected to motorized brakes. Registration marks on the film ensure cutting and sealing alignment. Heat seal jaws are PID controlled to maintain consistent seal strength. For rolls, twisted ends are formed using roller bars that compress the candy tube while rotating. The twisted sections are heat set to preserve shape. Cartons and boxes use cold form glue that is applied by nozzles onto folding flaps. Glue cure time is matched to conveyor speed and compression length. Cartons are held under pressure for 2 seconds to ensure bond strength. Filled cartons are buffered before case packing using a serpentine conveyor that absorbs flow variations. Cases are arranged in alternating layer patterns to improve stacking strength. Full pallets are weighed before wrapping to confirm case count. Throughout the Smarties production process, all mass transfer points are closed-loop systems to prevent material loss. Product handling uses gentle slopes and controlled angles to minimize breakage. Surfaces in contact with product are coated with anti-static and anti-stick layers. Production parameters are logged in real time, including syrup temperature, pan speed, air humidity, atomization pressure, print contrast, and packaging throughput. These values are compared to target set points every batch cycle. Waste product is collected at each rejection point and separated by type. Non-printed Smarties can be remelted and reused. Printed or overcoated pieces are ground and disposed of in a controlled waste stream. Jolly Rancher candies are produced by first preparing a concentrated sugar syrup, which serves as the structural base of the hard candy. Granulated sucrose is stored in silos and pneumatically transferred into batching hoppers positioned above stainless steel dissolution tanks. Liquid glucose or corn syrup is pumped from heated holding tanks and metered into the same batch tanks through insulated lines. The ratio of sucrose to glucose is fixed and varies slightly by flavor to affect hardness and glass transition behavior. Water is added last to the batch to begin dissolution. The tank uses an agitator with 3-blade impellers mounted on a vertical shaft that mixes all ingredients until fully homogenized. Tank temperature is held at 85 degrees Celsius to accelerate solubility without initiating premature boiling. Once dissolved, the sugar mixture is transferred to a continuous cooker via positive displacement pump. The cooker is a tubular heat exchanger that uses steam as a heating medium to bring the syrup to final cooking temperature. As the syrup flows through the tubes, internal temperature rises to approximately 160 degrees Celsius. This evaporates most of the water and converts the syrup into a thick, amorphous mass. The syrup exits the cooker under pressure and is fed directly into a vacuum chamber where remaining moisture is removed rapidly. Vacuum levels are controlled using a pressure regulator that lowers boiling point to minimize heat degradation. The product exiting the vacuum chamber has a moisture content of less than 2%. This highly viscous candy mass is discharged onto a stainless steel cooling table coated with a non-stick surface. A mechanical scraper arm moves the mass back and forth to reduce temperature and increase viscosity. Cooling continues until the mass reaches a pliable yet non-flowing state, typically at around 110 degrees Celsius. At this stage, acidulants such as malic acid or citric acid are added manually or through a heated dosing manifold. These acids provide the sharp fruit flavor profile typical of Jolly Ranchers. Simultaneously, concentrated flavor oils are added using a high shear mixer attached to the edge of the cooling table. Colorants are blended in at the same point and are selected to match each flavor. The flavoring and coloring step is brief because extended mixing can cause volatile loss. The candy mass is worked using mechanical paddles that fold and compress the batch until all additives are fully incorporated. This creates a uniform mass with consistent flavor distribution and visual appearance. The mass is divided into portions and transferred to a forming line using heated transfer arms. The forming line begins with a batch roller, which elongates the candy into a rope of constant diameter. The batch roller consists of 4 or 5 heated rollers that rotate in sequence and pull the candy through narrowing gaps. The temperature of each roller is individually controlled to prevent sticking. As the rope exits the final roller, it is passed through a rope sizer, which uses a die to shape the candy into an exact diameter. This diameter is based on the final desired piece weight and length. The rope is pulled forward by synchronized feed rollers, which deliver it into the die-forming machine. The die-forming machine consists of a rotating drum with recessed cavities. As the rope enters the drum, a knife presses it into the cavities and shears the candy at regular intervals. Each cavity is shaped like the final product and creates a pillowed form on the surface of each candy. Formed pieces are ejected from the die cavity using a release pin. Pieces fall onto a vibratory cooling conveyor that carries them away from the die head while further reducing internal temperature. The conveyor uses airflow and mechanical shaking to ensure the candies remain separated during cooling. Cooling continues until surface temperature falls below 40 degrees Celsius. At this point, the candy is sufficiently rigid to avoid deformation. Candies pass through an oiling drum where a small amount of anti-stick oil is applied to prevent adhesion during storage. The candies are then conveyed to a storage bin or directly to the wrapping line depending on production sequencing. The wrapping machine used for Jolly Ranchers is typically a high-speed twist wrap unit. Formed candies are fed into a flighted conveyor that spaces them evenly before wrapping. Wrapping film is fed from a roll and cut into segments that match the length of each candy. A film grabber aligns each piece of film with the incoming candy. The machine wraps the film around the candy and twist both ends simultaneously using 2 rotating fingers. The twisted ends are pressed to retain their shape. Wrapped candies exit the machine on a discharge conveyor and are grouped automatically into rows for further handling. Each component of the line operates continuously and in coordination with upstream and downstream modules. Flavor changeovers require the flushing of flavor oil lines and cleaning of the color tanks. The cooling table surface is scraped and cleaned before introducing the next batch. Each flavor batch typically corresponds to a specific production run to avoid cross-flavor contamination. Color consistency is maintained by using pre-blended pigment dispersions added through precision pumps. These dispersions are stirred continuously in a heated jacketed tank before injection into the batch. Volume dispensed is controlled by a pulse counter that records each pump stroke. Flavor strength is managed by load cell feedback, which calculates the candy mass and adjusts flavor oil volume accordingly. The oils are kept in nitrogen blanketed tanks to reduce oxidation during storage. Rope speed through the batch roller is monitored by encoder feedback and automatically adjusts based on temperature, mass viscosity, and die pressure. A thermocouple embedded in the rope housing measures product temperature before it enters the die head. If the temperature is too low, the feed rollers reduce pull rate to prevent rope breakage. If too high, the batch roller slows to allow cooling. The forming drum speed is matched to rope speed using a gear ratio that ensures clean cuts at every cavity. Cavity pressure is balanced using pneumatic tensioners to avoid candy flash or deformation. As the knife cuts each candy, pressure sensors detect load and ensure alignment. Misformed candies are diverted by an air jet triggered by machine vision sensors that detect dimension or position errors. The vibratory cooling conveyor has a zone design with separately controlled fans. Airflow is filtered and directed through baffles that create a laminar stream. The shaker speed varies by batch size and surface stickiness to optimize separation. Oiling quantity is regulated by metering pumps connected to a fine mist nozzle array. Only a trace amount of oil is used to avoid impacting flavor or texture. Excess oil is collected in a catch tray and recycled through an inline filter. The twist wrapping film is made of cellophane or oriented polypropylene and pre-printed with branding and flavor identifiers. Film tension is controlled by a feedback loop that adjusts brake pressure on the film unwind shaft. Knife blades that cut the wrapping film are positioned by servo motors that adjust cut length in real time based on candy dimensions. Heat sealing is not used on these wraps because the twist retention is mechanical. The wrapping process operates at up to 1,000 pieces per minute and includes redundant feeders to reduce downtime. Candy positioning is controlled by optical sensors that detect each piece and signal the film release mechanism. Throughout the Jolly Rancher process, thermal conditions are tightly regulated to maintain texture and gloss. Humidity is controlled in the cooling and forming areas to prevent surface fogging or sugar bloom. Runts are produced by compressing flavored and colored dextrose-based powders into shaped tablets using rotary forming presses. The process begins with the blending of base ingredients in large capacity ribbon mixers. Dextrose, which forms the primary bulk of the candy, is loaded from silos through vacuum transfer lines into the mixer. To this, a precise amount of maltodextrin is added using screw-driven feeders. Citric acid powder is added to enhance flavor sharpness and to balance sweetness. Calcium stearate is introduced as a lubricant to prevent sticking during compression. Microcrystalline cellulose is used to improve structural integrity and reduce friability. Each component is weighed automatically by load cell controlled bins before entry into the mixing chamber. Mixing occurs under low speed agitation for uniform distribution of fine powders. After dry blending is complete, a liquid binding solution is sprayed into the mixture. This binder typically contains invert sugar or corn syrup diluted in water to enhance adhesion during compression. Spray nozzles mounted at the top of the mixer deliver atomized binder in controlled bursts while the mixer continues rotation. The partially moistened blend exits the mixer and is transferred via auger to a fluid bed dryer. The dryer uses filtered air heated to approximately 60 degrees Celsius to remove excess moisture while preserving binder functionality. The drying process takes between 15 and 20 minutes and ends when the target moisture content of around 1.5% is reached. Once dried, the mixture is cooled to ambient temperature through a vibrating cooling conveyor fitted with perforated air plates. The cooled material is then screened using a rotating sieve to break up clumps and ensure consistent particle size before compression. Oversized particles are ground and reintroduced into the feed stream. The prepared mix is transferred to an overhead hopper, which feeds directly into rotary tablet presses. Each press consists of a die table that rotates horizontally with multiple tooling stations. As the table turns, powder falls into open dies, which are then compressed between upper and lower punches. Each die cavity is shaped according to the desired fruit design, such as banana, grape, or strawberry. The punches apply high pressure for a brief duration, which compacts the powder into a solid mass. Ejection cams raise the lower punch to release the formed candy, which is then pushed out of the die onto a discharge belt. Compression force, dwell time, and punch speed are continuously monitored by sensors on each press station. Press speed is generally between 40 and 60 rotations per minute, depending on candy size and complexity. Multiple presses run in parallel to produce different shapes and colors. Formed candies exit the press at a controlled rate and are transferred by belt to the coating drums. These drums are inclined and rotate slowly to tumble the candy pieces without damaging them. A sugar syrup is applied via a spray manifold mounted inside the drum. The syrup contains dissolved sugar, colorants, and flavor oils specific to each fruit variant. Application of the coating syrup occurs in cycles with drying air blown between each layer. The syrup forms a smooth, glossy shell around the compressed candy core. The drying air is filtered and maintained at a temperature of 35 to 40 degrees Celsius to prevent syrup crystallization. Each coating drum batch completes between 12 and 15 cycles before final gloss is achieved. Color uniformity is monitored using inline optical sensors mounted at the drum exit. Any candy that fails color threshold is automatically diverted by air jets to a reject bin. Accepted candies continue to the polishing stage. Polishing drums are similar in design to coating drums, but operate at lower speeds. A light mist of food-grade carnauba wax is sprayed onto the tumbling candy to enhance surface shine. Polishing continues for 5 to 8 minutes until all pieces achieve uniform gloss. Polished candies exit the drum onto a vibratory conveyor, which aligns them for inspection. A camera-based sorting system checks each candy for cracks, deformities, or uncoated surfaces. Machine vision algorithms trigger solenoids to remove defective units from the flow. Correct candies pass to a final drying tunnel where low humidity air circulates to stabilize the coating. Tunnel dwell time is approximately 3 minutes. After drying, the candy enters the counting and filling station. The filling machine uses rotating discs with pockets that hold fixed numbers of candies. Each pocket empties into a vertical chute leading into packaging units. Depending on packaging format, the candy is dispensed into cardboard cartons, plastic tubes, or small bags. Film-fed vertical form-fill seal machines receive candy loads by timing screw and funnel. The machines form packaging film into tubes, seal the bottom, drop candy, and seal the top. Each package is cut and dropped onto a belt, leading to collection bins. Plastic tubes are filled by inline auger fillers that rotate open-bottom tubes beneath product chutes. A single rotation dispenses a set quantity of candy. Filled tubes are sealed with heat or snap-on caps, depending on design. Cardboard boxes are filled on a separate line using drop gate fillers. Boxes are pre-formed using a mechanical folder and pushed through filling lanes. After filling, a flap tucker folds and glues the top closed. All packaging units pass under an inkjet printer that applies batch codes and timestamps. Packages are then grouped using collating conveyors and shrink-wrapped or cased based on distribution requirements. Throughout production, each shape and flavor batch runs in dedicated equipment zones to prevent cross-contamination. Banana-shaped candies are yellow and flavored with isoamyl acetate. Strawberry-shaped candies are red and flavored with ethyl methylphenyl glycidate. Grape, lime, and orange follow similar combinations of shape, color, and ester-based flavoring. Each flavor's syrup is prepared in separate jacketed tanks to preserve aromatic quality. Syrup concentration is adjusted to match coating viscosity for that flavor's specific sugar crystal structure. Color pigments are pre-blended in glycerin or propylene glycol and introduced during syrup preparation. The compressed candy core has a fixed porosity that allows coating to adhere without absorption. Compression tooling is polished and coated with anti-stick materials to maintain shape definition and reduce mechanical drag. Die cleaning is performed at regular intervals using brush systems that rotate within the die cavity. Punch alignment is verified using a laser sensor that checks deviation in vertical axis during operation. Air supply for fluid bed drying, cooling, and coating is sourced from a centralized HVAC unit with HEPA filtration. Ducting routes temperature and humidity-controlled air to each stage through pressure-controlled dampers. All rotary presses, coating drums, and polishing machines are synchronized via a central PLC that tracks product flow and batch progression. Any variance in throughput or processing time automatically adjusts downstream processes to maintain balanced output. Candy weight is checked at the end of the forming line using a dynamic scale belt. If a candy is too light or too heavy, it is removed before coating. Moisture content of coating is measured using infrared sensors to determine residual water before drying. Compression tooling for Runts is machined from hardened stainless steel and engraved with shape detail using CNC lathes. Replacement tooling is stored in temperature-controlled drawers to prevent thermal distortion. Punch lubrication is automated with small volume silicone oil injections at each cycle. Candy density is maintained at a specific range to avoid breakage during packaging. Too much compression leads to brittle texture, while too little causes shape distortion. Process control data is logged continuously and reviewed for each shift. At no point is the candy handled manually until fully wrapped or boxed. The entire line from blending to packing operates as a continuous feed with variable speed, drives that adapt to real-time conditions. Historically, gum base was made from natural tree resins like chicle, a latex-like substance harvested from the sapodilla tree, which grows in Central America. However, nearly all modern bubblegum factories now rely on synthetic gum bases. These are specially formulated blends of food-grade elastomers, resins, waxes, plasticizers, and softening agents. The use of synthetics provides far greater control over consistency, shelf life, and bubble blowing capability, which is critical for mass production and distribution. The raw materials used in synthetic gum base are delivered to the factory in large sacks or drums, and each ingredient is sampled and tested before entering the production line. Elastomers, such as polyisobutylene and polyvinyl acetate, provide the stretchy, elastic properties needed for bubble blowing. Resins act as binders that hold the gum together. Waxes, like paraffin and microcrystalline waxes, are added to soften the mixture and give the gum its pliable, non-brittle chew. Plasticizers such as glycerol, esters improve texture, while fillers like calcium carbonate or talc give the gum body and density. Each of these materials must be prepared for mixing. Solid components are broken down using industrial grinders and micronizers to achieve a uniform particle size, which ensures even distribution throughout the base. Waxes and resins are often pre-melted in jacketed stainless steel tanks equipped with indirect heating systems to prevent scorching. The raw elastomers are delivered in dense, rubbery blocks that are cut down using industrial dicing equipment before being added to the mix. Accuracy in measuring each component is vital. The slightest deviation in the amount of resin or wax can drastically alter the final chewiness and bubble-forming capability of the gum. Now it's time for the blending of the gum base, which happens in large Sigma blade mixers, named for their two interlocking Z-shaped blades that rotate in opposite directions to fold and knead heavy materials. These mixers are specifically designed to handle high viscosity compounds like gum base. The various pre-measured ingredients are added to the mixer in a specific sequence. First, the elastomers are introduced and given time to soften and break down under shear force. As they begin to form a uniform mass, resins are added to bind the structure. Waxes and plasticizers follow, blending smoothly into the mixture to help reduce internal friction and improve processability. This mixing process is not quick. Depending on the size of the batch and the recipe, the blending cycle can last anywhere from 45 minutes to several hours. The mixer itself is equipped with internal thermocouples to continuously monitor the temperature of the mass, which is maintained between 60 degrees Celsius and 90 degrees Celsius. Too low and the materials won't melt and blend. Too high and thermal degradation could occur, affecting the safety and performance of the gum. Operators observe the process through viewing ports and rely on torque readings and viscosity data from the mixer's internal sensors to determine the exact moment the gum base is fully homogenized. Once the gum base has reached the correct consistency, it is discharged from the mixer. This is a challenging step because the base at this point is extremely thick, sticky, and hot. To facilitate removal, the bottom of the mixer opens hydraulically and the heavy base is dropped onto a large stainless steel cooling table or fed directly into a sheeting system. The cooling table is actively temperature controlled using circulating chilled water to begin lowering the temperature of the gum base as quickly and evenly as possible. Large Teflon-coated rollers may be used to flatten the mass slightly, increasing surface area and speeding up the cooling process. The goal at this point is not to bring the base down to room temperature entirely, but to reduce its temperature to a workable range, usually between 40 degrees Celsius and 50 degrees Celsius, so it can move to the next stage without sticking to equipment or losing its plasticity. The partially cooled gum base is then cut into manageable blocks using high lubricity heated cutting blades. These blocks are weighed, labeled with batch numbers, and either sent directly to the next phase of production or stored in temperature-controlled holding rooms for later use. Even in this early stage of production, quality control is already an active part of the process. Samples of gum base are collected from each batch and taken to the plant's in-house laboratory, where technicians test them for elasticity, tensile strength, softness, and melt behavior. Specialized equipment such as rheometers, durometers, and texture analyzers are used to measure mechanical properties under simulated chewing conditions. This ensures that the gum base will respond correctly when blended with sweeteners, flavors, and colors in the next stages of processing. It's also worth noting that not all gum-based formulations are the same. For bubblegum specifically, the formulation includes higher levels of elastomers and plasticizers than in chewing gum intended for long-lasting flavor or dental benefits. Bubblegum is designed to be more pliable and capable of trapping air, so it can form large bubbles without breaking too easily. This performance requirement influences everything from ingredient selection to mixer settings and even downstream cooling methods. Therefore, each variation of gum base may require its own unique process settings and equipment parameters. In the next stage, the base will be transferred into another high-capacity mixer, this time designed to handle not only dense material, but also sensitive flavor components and volatile sweeteners. The balance of heat, pressure, timing, and sequencing here is critical. Too much heat can break down sugar molecules and destroy flavor integrity. Too little, and the gum won't mix properly. The entire system must operate like a symphony of mechanical precision and food engineering science to ensure that every piece of bubblegum delivers the iconic chew and flavor burst that consumers expect. With the gum base now fully prepared, cooled, and tested, it's time for one of the most critical stages in bubblegum manufacturing: the integration of sweeteners, softeners, and flavorings. This is where the bland, rubbery core transforms into something enjoyable and familiar. The sweet, fruity, chewy product capable of inflating into perfect pink bubbles. At this point, the gum base is still a nondescript mass, pliable, tacky, but utterly flavorless and unappealing. The magic is about to happen in an industrial mixing process that must blend these next components evenly while preserving the precise texture and chew required for successful bubblegum performance. Before anything is added to the gum base, it must be brought back to a specific working temperature. Though the blocks were cooled after being discharged from the original base mixer, they must now be re-softened for further blending. This is accomplished using a series of jacketed holding vessels or warming conveyors that apply gentle, indirect heat, usually via hot water or steam circulating through double-walled stainless steel pipes. The temperature is carefully raised to a range of 40 degrees Celsius to 60 degrees Celsius, just enough to make the gum base pliable again without overheating or causing degradation of any of the soon-to-be added ingredients. The re-softened gum base is then introduced into a second type of mixer, often a horizontal batch mixer or a planetary mixer specifically engineered to process high-viscosity food materials. These mixers are outfitted with double sigma blades or paddle arms capable of kneading the gum base with immense force. Once the gum base begins to rotate and fold, the sweeteners are added gradually. These include powdered sugar, also known as icing sugar, glucose syrup, and sometimes corn syrup solids. Each of these sweeteners serves multiple purposes. Powdered sugar provides bulk, texture, and long-lasting sweetness. Glucose syrup contributes a softer mouthfeel and prevents crystallization. Corn syrup solids help maintain chewiness and shelf stability. In some formulations, especially those designed for sugar-free bubblegum, bulk sweeteners such as sorbitol, xylitol, or mannitol are used in place of sugar. These polyols require different handling due to their moisture absorption characteristics and sensitivity to heat. In any case, each type of sweetener must be fed into the mixer in stages, allowing the gum base to fully absorb and integrate the new material before more is added. This prevents clumping and ensures that the resulting mixture remains smooth and pliable. Industrial scale screw feeders or vacuum conveyors may be used to introduce these ingredients directly into the sealed mixing chamber to maintain cleanliness and prevent contamination. Following sweetener addition, softeners such as glycerin and vegetable oils are introduced. These materials are essential to prevent the gum from becoming brittle over time and to give it the desirable, soft, elastic texture that bubblegum is known for. The quantity and timing of softener addition are precisely calculated. Too little and the gum will harden quickly after production. Too much and it will become greasy and sticky, especially under warm storage conditions. Glycerin, in particular, helps trap moisture within the matrix of the gum and acts as a plasticizer, allowing the final product to retain its chew even after prolonged shelf life. Once the bulk of sweeteners and softeners are integrated, it's time for one of the most delicate and carefully timed steps in the entire production line: the addition of flavorings and colors. Flavor compounds used in bubblegum are typically a blend of fruit, esters, vanillin, and long-lasting artificial flavors engineered specifically for gum applications. These flavors must be oil-soluble and thermally stable, as any degradation can result in bitterness, loss of intensity, or altered taste profiles. The most iconic bubblegum flavor is a blend of banana, cherry, cinnamon, clove, and wintergreen, artfully balanced to create that familiar pink taste that people associate with classic bubblegum. These flavoring compounds are often concentrated liquids or emulsified pastes, and they're introduced in the final stages of mixing to preserve their volatile aroma compounds. If added too early, the heat and shear of the mixer could evaporate or chemically alter them. The flavors are poured in slowly while the mixer runs at a reduced speed, allowing gentle incorporation. Some manufacturers use pre-encapsulated flavor beads that dissolve slowly during chewing, extending flavor release over time. Coloring agents are added simultaneously or immediately after. These are usually food-grade dyes, such as Red 3 or Red 40, depending on regional regulations, and are added in liquid form or as pre-dispersed powders. These colorants are not just about visual appeal, they help consumers identify and associate flavor with appearance. For classic bubblegum, the universal hue is a bright bubblegum pink. The dye must be evenly distributed throughout the batch, and to do this effectively, the mixer must achieve total homogeneity without overworking the gum or exposing it to heat that could cause the color to fade or change. During this final blending stage, the entire gum mass is constantly monitored. Operators inspect the mixture for uniformity, gloss, elasticity, and color consistency. Samples may be extracted from the mixer at regular intervals and manually kneaded or stretched to ensure no streaking or spotting. Texture and pliability are tested by compressing and stretching a small piece by hand or using mechanical texture analyzers. If any inconsistency is found, whether it's too stiff, too soft, uneven in color, or lacking in flavor, the batch may be reprocessed or scrapped entirely, depending on the deviation severity. Once the gum reaches the desired final formulation, it's discharged from the mixer onto a temperature-controlled rolling table. At this stage, the gum has taken on its familiar look and feel: soft, elastic, vibrantly colored, and bursting with aroma. However, it's still a massive block of uncut material, far from the small, uniform pieces sold in stores. To prepare it for shaping and portioning, the gum is flattened using motorized rollers that compress it into thick sheets. These rollers are heated just slightly, enough to keep the gum pliable, but not so hot that it becomes sticky or begins to sag. The sheeted gum is then conveyed into a sizing line, where it passes through multiple sets of progressively narrower rollers to reduce the sheet thickness to the exact target for the final product. Whether the gum will be cut into strips, rolled into tape, molded into spheres, or formed into pillow-style pieces depends on the final product format. The sheet thickness must be precise. Too thick, and the gum will be too large to chew comfortably. Too thin, and it will tear or lack substance. Precision slitter blades then slice the gum into long ribbons, which are cooled again on conveyor belts using ambient air or chilled tunnels. These ribbons are stacked and allowed to rest briefly in temperature, tint, and humidity-controlled zones. This rest period, sometimes called the conditioning phase, allows moisture and elasticity to equilibrate across the entire piece of gum. It helps stabilize the internal structure and prepare the gum for cutting, shaping, and packaging without causing cracking or deformation. At this point, bubblegum is fully formed in its raw shape, but still unwrapped and unpackaged. The product is ready for the next phase, which involves high-speed forming machines, wrapping systems, and final packaging lines designed to handle thousands of pieces per minute. These systems require their own precise engineering and synchronization to maintain the integrity and appeal of the final product. Now that the bubblegum has been properly flavored, colored, sheeted, and rested, it enters one of the most mechanically intricate and visually satisfying stages of production: shaping and cutting. At this point, the gum exists in long, flat ribbons of pliable, glossy material, carefully rolled and stacked in conditioned zones to ensure uniformity and stability. These ribbons are conveyed in single file onto a forming line that uses high-speed, synchronized mechanisms to turn raw sheets into the iconic forms consumers recognize, whether small pillow-style pieces, sticks, chunks, tape rolls, gumballs, or extruded logs. Let's first explore the most common format, the pillow-shaped bubblegum piece. This format is familiar from vending machines, Halloween candy mixes, and individual wrappers. To achieve this, the bubblegum ribbon is fed into a forming wheel, where it is gently guided through a series of progressive molds or cavity rollers. These rollers are designed with alternating male and female cavities that press into the gum from both sides, creating the shape of a small rectangular block with softened edges. As the ribbon passes through these molds, the gum is compressed and cut simultaneously by a synchronized die cutter positioned just after the final molding wheel. Cutting must be done with extreme precision, as even a millimeter of deviation could affect packaging alignment and product weight. To account for thermal expansion and gum elasticity, the cutting blades are adjustable in both depth and cycle timing. High-speed optical sensors detect the flow rate of the gum ribbon, feeding data into a digital controller that dynamically calibrates the cutter's speed in real time. The gum, now formed into uniform bite-sized pieces, is ejected onto a short conveyor, ready for wrapping. In the case of bubblegum stick formats, like the flat rectangular pieces found in classic packs, the shaping process is slightly different. Instead of molding with rollers, the gum sheets are trimmed on all four edges to create clean, sharp lines. They are then passed through a rotary cutter equipped with hardened steel blades, slicing the sheet into strips of exact dimensions. These strips are stacked and cut again to create individual sticks. The machines responsible for this operation resemble guillotines, but with servo-controlled precision that allows for continuous, non-stop operation at high speeds. The final sticks are conveyed into wrapping units without any manual handling, preserving hygiene and maintaining throughput. Bubblegum tape, a novelty format often rolled into small plastic canisters, requires its own unique process. The sheeted gum is passed through a winding station where it is gently rolled into a flat coil, not unlike a roll of tape. Tension is carefully controlled here, too much pressure, and the coil will deform or stick to itself. Too little, and it will unravel inside the container. Once coiled, the tape is automatically dropped into a custom-formed plastic shell, usually hinged with a pop-top lid. A blade inside the lid allows consumers to tear off a desired length. These plastic cases are injection molded on-site or sourced in bulk and fed into the filling line by vibratory bowl feeders. For gumballs or spherical bubblegum formats, the production method is even more specialized. Instead of being formed from ribbons, these are made using extrusion and spheronization techniques. Warm gum is extruded through a nozzle into a thick rope, which is then cut into small segments by a rotating knife. These segments are dropped into rotating pans, lined with friction-inducing surfaces that tumble the gum continuously, rounding the pieces into spheres through centrifugal motion. Once the balls reach a near-perfect shape, they are cooled and coated in a separate process, which we'll explore shortly. Regardless of the final shape, all bubblegum formats at this stage are unwrapped and uncoated, meaning they are vulnerable to sticking, moisture absorption, and contamination. Therefore, the next critical phase is the wrapping and packaging process, which combines high-speed automation, material engineering, and branding considerations. Starting with pillow pieces and sticks, the gum is immediately conveyed into primary wrapping machines. These are high-speed horizontal or vertical flow wrappers, capable of wrapping hundreds of pieces per minute. A continuous roll of printed film, typically made of polypropylene or foil-backed paper, is unwound and fed through the machine. As the gum pieces travel along a conveyor, the film wraps around each piece and is sealed using heated crimpers that create a back fin seal and two end seals. For some classic styles, twist wrapping machines are used instead, which pinch both ends of a small rectangular wrapper and twist them tightly around the gum. These machines are equipped with sensors that detect gum position and length, ensuring perfect alignment between the product and its printed branding. If even a single wrapper is misaligned or improperly sealed, that piece is ejected from the line via pneumatic diverters. Wrapped pieces are then collected, counted, and transferred in bulk to secondary packaging machines. Secondary packaging is where individual units are grouped for retail sale. For stick gum, this may involve stacking 5 or 10 wrapped sticks into a flat paperboard sleeve, then shrink wrapping the pack. For pillow gum, machines automatically count the desired number of pieces and drop them into a pre-formed bag, which is then sealed using heat or ultrasonic welders. Packaging films are chosen for durability, oxygen resistance, and visual appeal, and often include tear notches or resealable zippers for convenience. In the case of bubblegum tape, filled plastic canisters are labeled and moved through a shrink sleeve applicator, which places a heat shrink label around the container. This sleeve serves both branding and tamper-evident functions, and is tightened using a controlled burst of steam or radiant heat. Finally, canisters are packed into display boxes or larger cartons using robotic pick-and-place arms. Now we return to gumballs, which undergo a unique finishing step: sugar coating. Unlike other formats, gumballs are coated in a hard, shiny shell that not only protects the gum inside, but also adds flavor, color, and gloss. This process is performed in large stainless steel coating pans that slowly tumble the gumballs while successive layers of syrup and powdered sugar are applied. The syrup typically contains water, glucose, and food coloring, which adheres to the surface of each gumball. Then a layer of sugar or sugar alcohol-based powder is sprinkled over the syrup, sticking to it and gradually building up a thick shell. Each coating layer must be dried before the next is added. Warm air is blown gently into the pans while the gumballs tumble, ensuring even drying without cracking or warping the shell. After multiple layers are built up, sometimes more than a dozen, the gumballs are ready for polishing. This final step involves applying a thin layer of food-grade wax or shellac to the gumballs to create the glossy, reflective finish that's so iconic. The polished gumballs are then cooled, inspected, and fed into bulk bagging or capsule dispensing systems depending on their final use. Throughout the forming, wrapping, and packaging process, real-time quality control continues at every junction. Vision inspection systems verify wrapper alignment, seal integrity, and color consistency. High-speed checkweighers ensure that every package contains the correct number of pieces and meets the stated weight. Metal detectors and X-ray systems scan for any foreign particles or processing defects. If a flaw is detected, the package is automatically ejected and flagged for review. And behind all of this automation is a digital infrastructure tracking every batch, from base production through to final packaging. Every piece of bubblegum can be traced back to the exact shift, mixer, raw ingredient lot, and even the machine operator responsible for that run. This traceability system is essential for food safety, quality assurance, and regulatory compliance. Once bubblegum has been fully processed, formed, wrapped, and inspected, it enters the final phase within the factory: storage, quality verification, and preparation for shipment. Although the gum is now finished, it still requires careful handling to ensure that its quality and integrity remain intact all the way through to its final retail destination. The post-production environment is just as controlled as the manufacturing zones. Finished goods are transferred into climate-regulated storage areas, where temperature and humidity are strictly maintained to preserve the texture, flavor, and packaging condition of the gum. Each product pallet is labeled with QR codes or barcodes that carry essential traceability information: product type, batch number, production date, and expiration code. These codes integrate with warehouse management systems that organize inventory by shelf life and destination. The warehouse operates on a strict first in, first out (FIFO) system to make sure the oldest products are shipped first, reducing waste and ensuring consistent freshness in the marketplace. Before any product is released for shipping, quality control teams perform final checks. Samples from each lot are pulled and tested for packaging seal integrity, gum softness, visual consistency, and flavor. Any package that fails inspection is flagged, and the rest of its batch is reviewed. All quality records are logged digitally, tying back to the original gum base formulation and mixing parameters. This robust traceability ensures that, in the rare event of a defect or recall, every package's full production history is instantly accessible. Once cleared, the products are palletized and prepared for outbound delivery. Some are shipped to retail distributors, others to vending machine companies, export terminals, or wholesalers. Trucks used for transport are checked for cleanliness and proper loading temperatures to ensure the gum isn't exposed to heat or humidity during transit. Stretch-wrapped pallets are loaded according to weight and stability guidelines, scanned out of the factory system, and then dispatched. Even after leaving the facility, each batch of bubblegum remains traceable, monitored, and accountable. This level of post-production oversight is essential to maintaining brand reliability and consumer trust. It ensures that the bubblegum purchased in a corner store, supermarket, or theme park tastes exactly as intended: sweet, chewy, stretchy, and perfectly made. From polymer blending and base formulation to flavor integration, shaping, wrapping, and final logistics, the entire bubblegum production process is a seamless combination of food science, mechanical precision, and quality management. It's a surprisingly complex journey for a product designed to be fun and carefree, proof that even the most playful confections are supported by a foundation of serious, sophisticated industrial engineering.